Welcome to the Propeller 2 live forum. This is the third part of the JonnyMac Presents Holiday Spin 2 Kit Programming Series. Johnny, are you with us? JonnyMac, that is. I trust he's out there.
I am here. Sorry, it's been a bit of a scramble today, and I don't know if you noticed it when I turned on my camera, I wasn't there. And I was wearing a blue shirt, so I thought that it was just deleting me. So I went and changed my shirt, and then I came back and I found I had a piece of blue painter tape on the lens.
Oh, and you found yourself.
And I found myself. Yeah, hey, he's back with a black shirt, which is my typical wear anyway.
Well, glad to see you, John.
Thank you.
Yesterday, if you're interested, we hosted a P2 Live forum where we had two really good topics. The first one was Kevin sharing his P2 marble run, and I posted a link to the YouTube video. And he also gave us a tour of his workshop, and his parents told us about when he ordered his first circuit board from China, which was a good story. So that was the first part of it. The second part was the Hub 75 LED plans from the P2 Live forum and how that's progressing. So if you watch the video, you'll get two for the price of one. That's posted. The link is pasted there. Today, by the way, y'all know this, but we're using these parts. They're still available. I think we have a dozen. We just kind of keep adding them as the parts dribble in from Amazon, as y'all know. And this came into stock as well finally today. This is made by Stephen Morocco. This is the Hub 75 LED driver adapter board that plugs onto the JonnyMac, the Propeller 2 evaluation board, and the P2 mini breakout board. And we are just working on getting the panels in. We're ordering 100 of them from China and hope to have those maybe before Chinese New Year. We're getting started a little bit late, but we'll let you all know. Today, John is ready to get started. And as usual, I'm going to post the Buy John a Coffee link into the chat so we can all go do that. And Parallax has bought him a few coffees as well today, but he drinks a lot of coffee and eats a lot of sushi, so make your deposit in the bank of JonnyMac. All right, John, are we ready?
Okay, thank you, Ken. You're ready for me?
We are ready for you.
All right. Hello, everybody. Happy New Year. This is the first since the New Year. Dennis, I have a question for you at the end.
Okay.
I will ask your forgiveness. I am a little haggard it'll take me just a second, said, and I literally finished everything 10 minutes ago. Now, I finished the files earlier. Did everybody get the files? Okay, good. I think, as soon as I say this, I know something's going to go wrong, but I think you'll enjoy the files. I'm really kind of excited because we're talking about I2C today. And it's funny, I2C is very simple and it's become ubiquitous, but that's a good thing because you can find just a boatload of things, sensors, devices. For example, I got two in my hand. So here, this little dude is an encoder. Now, we know how to read encoders on our own. This one is made by SparkFun, has a little processor on it so that you can have a whole bunch of these on two wires with I2C, and it also has LEDs in it. It's expensive, but it does work. And we're going to talk about, I'm going to show you some neat stuff from this. Another SparkFun item. This is a little 7-segment display, but it's I2C. So, that way on a 7-segment display, we would have 4 times 8 plus a couple of extra. That's a lot of I/O pins, but this takes it down to 2 plus power. So there's lots and lots and lots of neat sensors and accessories and devices that you can find. And what you're going to find is it's a really simple protocol to learn and to understand. Now, the good news is I've written drivers. I see my friend Mike Green, he's on screen. He's got a nice driver out too. There's plenty of drivers, so you don't have to worry about the low-level stuff unless you want to try it yourself. And I will say that myself and lots of other people put out drivers. I will always encourage you to try to write your own. It's even if something exists, because you'd say, geez, I can go buy bricks at the lumberyard. I don't need to make a brick. Well, you learn a lot about bricks by making a brick. And so you might only do it once, but it's a worthwhile learning experience. So my driver, is included in the files. You have that. Again, Mike has written an I2C driver. There are lots of them out there. Once you understand the elements of I2C and how they come together and you see how easy it is, then anytime you pick up a new widget from a vendor that says, hey, this is I2C, you'll know how to deal with it and you won't have any problem. Here's what I want to get to is there sometimes is our habit as humans to say, hey, where's the object for widget X? I want every one of us to be in the attitude of, I don't need no stinking object. I can write it myself and then give it to the community and be a contributor. Okay, so shall I share my screen and stop being silly? Share. Okay, hopefully you'll see my PowerPoint.
Yep.
Okay, and I'll just leave it in this mode. So I2C is a protocol. Oh well, it's a hardware system that has a protocol. I2C is actually a contraction for IIC. I2C is easier to say, and IIC sounds like something a pirate is yelling. So I2C, but this is what it stands for, is inter-integrated circuit. And it was created so that on a circuit board, we could connect lots of chips using only a few lines. And I'll show you an actual example. I showed this in one of my other presentations. This giant board is an industrial controller. Now, obviously, this is a prototype. There is lots of stuff going on here, and we have lots of I2C parts so that we can talk to them with, this has got a P1 on it. So there's not as many IOs as say we have on the P2. Using I2C, we were able to expand that. It was designed by Philips almost, well, I guess this year would be 39 years, so it's been around a while. Here's the definition and kind of the mouthful, and we'll break this down. It's a half duplex, sorry, I can read my own writing, half duplex, open collector, open drain, 2-wire synchronous serial bus. Here's what all that means simply. Half duplex means we can all, one thing talks and then listens. So it's like this. There's only one person that's talking at a time. That's half duplex. Our serial drivers and things like that, we can have both things talking simultaneously. We can send and receive at the same time is what I mean to say. With I2C, we can only send or only receive. We can't do both processes at once. That's half duplex. Now, open collector, open drain, everything's open drain these days because we're using FETs, but what that means is that on those two wires that we have, the only thing we can do to them to affect them is to pull them to ground. And so the immediate thought becomes, well, okay, if I can only pull it to ground, how do I get it up to VCC so that I have a 1? We do that with an external pull-up. And so if you ever see open collector, open drain, you have to know that there's going to be a pull-up somewhere. Now, in the old days, and even with the P1, we have them on the outside of the chip. The P2, we can enable pull-ups on the inside, so we have a choice there. And let me just show you, I pulled up a diagram from one of the parts that we'll see. Can everybody see this PCF 8574 diagram?
Yeah, it's clear.
You should see a schematic looking thing on my, all right. So here is our controller, and here's that device. But you see, here's the 2 pins that we care about, is the clock and the data line. And you notice they have pull-ups. So when we want to have a 0 on either of those lines, we pull that line to ground. When we want a 1 or a high on either of those lines, we float the input or we release it. It's like opening a switch, and then the pull-up will take the line high. Now, the reason for this is important because it allows these multiple devices on the bus to not have a conflict with each other if there is an error somewhere. So for example, if two devices try to pull the bus low at the same time, well, both are trying to pull to ground, so there's no short circuit. But if you have a driven system where one device is trying to drive the bus high and the other one's trying to pull the bus low, you'd have a short circuit and you could have a circuit problem. So that's why this topology is used. It's common in a lot of places. Next week, we're going to be dealing with the one-wire sensor. It does the same thing. So it's a very common strategy. Any questions on that open collector, open drain kind of thing? It's used a lot in sensors too, and it allows systems of different voltages to communicate with each other very easily. Okay, we all just discussed it's two wires, and we call them SCL and SDA for their clock and the data, is what those mean. And it's synchronous, which means that the serial data that is going back and forth on the bus is synchronized to a clock. The clock in I2C is always controlled by the master. Okay, so that's going to be us. The P2 is going to be the master in all the transactions. Now, I2C can tolerate multi-masters. So you could actually have multiple masters on the same bus talking to everything. My driver is single master only. So if you want to do multi-master, that's something you'll have to explore elsewhere. I've never needed it, to be honest. But that is available within I2C. So again, as I said, the reason that I2C was developed was to allow a processor or a master device on the bus to talk to a lot of things with very few wires. So if SPI is another bus topology that's very, very common. Now in SPI, which stands for Serial Peripheral Interface, we have a clock, we have data out, data in, and then a chip select. So the minimum number of pins that we would have in a SPI system is 4, and that's for one device. For every other device that we add, we have to add another chip select. So let's say you had 4 devices that you wanted to talk to via SPI, you would have the clock and the 2 data lines, and then you would have 4 chip selects. So that would be 7 IO pins would be consumed in that situation. Now, there are trades, and as engineers, we're always making decisions. SPI is very fast. And so, that's its benefit. Now, its cost, it's not so cool, is it takes a lot of IO pins. I2C is not very fast normally. It's getting better and better, but it's fairly slow in the scheme of things. But you can have, you'll see it, the people say you can have 127 devices on the bus. That's not a real practical thing, but you'll see why they say that because of the addressing. Now, interestingly, going back to this industrial board, this has a bunch of SPI, this has a bunch of SPI devices on it. What we did in order to kind of make things work nicely is we use I2C to create a whole bunch of chip selects so that we could talk to all of these SPI devices. So we mixed the buses together, and that gave us, there's a lot of IO on this process, on this board, and it's going to 1P1. We did that by mixing those topologies. It worked really nicely, and this is a product that's in production. So as I was saying, in this scheme of I2C, we have the data in the clock line, the master controls the clock. Now there's a caveat to that. There is a feature in I2C called clock stretch, which allows the slave device to say to the master, hey, slow down. And it does that by holding the clock low before the master can release it high. And it's funny, there was a conversation in the forums recently, we're saying, yeah, all these chips are really fast, nobody does that. I ran smack into it with this thing when I was working with Casey on it. It would sometimes work and sometimes not. And I found out, and I'll show you how I found out, that this uses clock stretching because it's not an I2C chip on here. It's a little, very small, low cost, very slow microcontroller. So they're synthesizing I2C the way that I am, although I have a much faster controller. And it just needs more time for some of the transactions. And so I ended up putting that back into, you know, the funny thing is I had clock stretch in, I took it out. So it's back in and it'll work with this device. In fact, there is a bonus demo in the files folder that starts with 99. It's to demonstrate this thing if you want to play with that. You'd have to order one from SparkFun though. Any questions so far? We have very few slides today because we're going to get right to code. Okay, within an I2C transaction, there are 4 things that can happen. We have a start event, which tells the slaves, get ready, here comes some traffic. We can write, and we'll show you that transaction. We can do a read, and when everything is done, we do a stop, so which tells the devices, okay, we're finished talking now. That's it. Those 4 elements are there. So if you look inside my driver later, you'll see stop, write, read, start, write, read, and stop. Now, because it's a little easier and I2C allows it to read or write a big block of bytes from a device or to a device, I have read block and write block in there as well. So there's really only 6 things going on after setup. It's a very, very simple object. And from there, you can create anything with it that understands I2C. On write, and we are talking about 7-bit addressing in this scheme. There, you'll see in I2C documentation 10-bit addresses. It's not common. I've never run into it myself. But we're talking about devices with a 7-bit address, although I show them as 8 in my code. You'll see it in a minute. And each transaction, a write or read, has 9 bits. There's the data, and then there's an acknowledge, an ACK, or a NAC. And those are important to the way the data is flowing. So in a write, the master controls the SDA and the data pin and the clock. In a read, because all of this, remember, is we're focusing on the master. The read also 8 bits plus an ACK-NAC, but forgive me, I have a typo in my slide. Thankfully, I didn't put them out. The master controls SCL, and oh, sorry, this is, there we go. Forgive me, I told you I was frazzled today, and I'm very sorry for that. In a read, the slave is going to be manipulating the data pin. The master is still controlling the clock. So remember, the clock pulse generation is always controlled by the master. The only thing the slave is going to do is hold that low if it needs to slow down the transaction. But again, unless you're using a microprocessor-based device, you're probably never going to see that. So these are the events. Start, we both go high, then in the SDA goes low, and then the clock goes low. That order of those things happening is what tells the state machines in the I2C device that, hey, we have a start, and now we're going to be listening to the bus. If you look into I2C documentation, you're going to see diagrams like this, and you'll want to get used to them. They tell you everything you need to know. So as I said, and you probably assumed, the start condition is what gets a transaction going. Once we've generated a start, the bus needs to know who's being addressed. And so that happens through the control byte. That is the identifier of what device that is hanging on the bus of all these things that could be out there. That's who we want to talk to. Everything else that doesn't match that should shut down. So this is important. You cannot, or you should not ever have 2 devices with the same exact slave ID on the bus, because if you do, there will be a conflict. They'll both try to be writing back. After the control byte, now you'll notice I'm going to show you a better diagram here. This last bit tells us if we want to write or read the device. So 0 is for write. So you see that low condition there means this control byte is set up for a write. Then the acknowledge comes from, this is coming from the external device. So we will write the 8-bit ID, which is the 7-bit ID plus the read-write bit, and then the next clock bit should be a low, an acknowledge. So in this system, acknowledge is low. If it doesn't respond, then we will have a high when we do that 9th bit. And this makes sense, right? Because remember, the bus is being pulled high by a resistor. If a device isn't there, it can't pull the device low. So when we do that 9th clock, the bus will be high. So NAC is high, ACK is 0 because we're actively pulling it low. Now, the next section is going to be dependent on the device. This particular diagram is from the EEProm that is on the little clock module that's in your kit. And it has a 12-bit address. So the first word after the write is this is going to be the upper 4 bits of the address. Then we're going to send the lower 4 bits. Now, this particular diagram is for a read. If it was for a write, we would just start writing the bytes. In a read transaction, we restart the bus and we send the control byte again with the last bit high, which tells it to read, and then we read the data back. This will make more sense as we go through. I'm going to show you in the code. Here's that control byte we talked about. Now, I2C devices have 2 elements in their slave address. This 4 bits is what kind of thing it is. This is an EEProm. So if you see 1010, it's an EEProm type device. There are several other devices that have that, because you can imagine there's a gajillion device types in the world, and we only have 4 bits to describe them all. So there's lots of shared there, but this is very common. You'll see that in EEProms. If you have a Propeller one, you've probably already seen that if you've done anything with I2C. Now, the next 3 bits are the address for that thing. This is to say then, for this device type, we can have up to 8 of them on the bus because we have 3 bits. Now, not every device will use all 3 address bits. In fact, some devices like RTCs don't use them at all. So this will always be 0. But in the case with EEProms, for example, which I use all the time, you can have multiple EEProms to expand storage space by putting them on the bus and then configuring the address pins on the physical device. So these address bits are connected to pins on the physical device. If you look at the device, in fact, if we see over on that, remember this diagram, you see, here's the PCF 8574, which is on the LCD. You'll see there are 3 bits here for the address, and they're all connected to ground. So that would set this device to its type plus an address of 0. All right. So that's going to be important. I'll show you how I deal with it in code. And then this bit is going to change during the transaction. Initially, we're going to start with a write, but if we want to read back, then we're going to change this bit. And again, this is the acknowledge. So I know I'm going a little fast because I want to get into fun code. Is there any questions? Okay, so remember, it's a 2-wire bus. One thing talks, the other thing can talk back.
One question from Facebook. In the case of ill-behaved I2C devices, what happens if one of them tries to force the SDA line low and the Prop2 smart pin tries to go high, or vice versa?
Well, it won't hurt anything. I mean, it might clobber the transaction, but if it's, as long as your code that is driving the SDA is not using the output driver, direct output driver, it's using the pull-up type thing, again, your transaction might get blown up, but your chip won't get blown up because of that open collector topology. Now in the P2, it's a little confusing because we have pull-ups inside, and you'll see the code actually says drive the pin high, but the configuration says, yeah, but do that through a resistor so it's behaving like a pull-up. So again, the open collector bus, that style of bus, is what saves us here. If something misbehaves, again, the transaction might get smashed, but the devices won't be harmed. You know, there's no chance for a short circuit if everybody is designed properly. Now, you have case, you know, for example, the P1, to be honest, violates this, that the P1, when it boots, it drives the clock high and low. In I2C, you're not supposed to do that, but you know, it's probably not thought about. And I've never had a problem. Nothing has ever been harmed, but you want to be careful when you're writing your own I2C code. Don't drive the either pin high or high. Just pull it low. Let the pull-ups take it high.
Thank you.
Mm-hmm. Okay, here is an actual I2C transaction from a real device. It's this thing. Now I've got close-ups of this, but I want to show you this is a real thing. When I was having trouble getting the code to work for this, like I said, it was kind of janky, kind of like in that last question. What I did was I put a logic analyzer on the bus and recorded it to see what was going on. And I'll tell you what's happening with the colors, and then I'll show you in a close-up. But here's the start transaction, and this is writing the address to it. This is a bit of data that's going along. This is a register here. This is an acknowledge, that's an acknowledge. Here is a stop, because this is actually a read transaction. And then here's the new ID in read mode. But you see this big, long space where the clock, the clock line is stopped, it's white. You see this line is pulled low. This is the clock stretch. The device, this thing was holding the clock line low. And what you have to do in your driver, now mine does that. So if you're gonna write your own driver, when you've written, before you look for the acknowledge bit, you want to make sure that the clock line is high. Now, it's really simple to do because you're just releasing the clock line so that it creates the next pulse. But what you have to do is look to see, after you've released it, you have to verify it went high. If it didn't, it's because it's being held low by the external device. So you just wait for that process to finish. When the clock goes high, as you see it did right here, then you can move on. So this is a real world clock stretch situation, which I had never seen before. And now, again, that happens because this is not, this doesn't have I2C hardware on it. It's being synthesized in a really small, not very fast microcontroller. And it needed time to get this data. This is the 2-byte response packet that I was looking for. So here's a bit of a close-up of the start of that transaction. So here you can see, now the nice thing about I'm using a piece of freeware that's really very nice called PulseView, and it has protocol analyzers in it. So this stuff is created by PulseView. It knows I have I2C, I've told it that. And so it says, okay, here's a start condition. And as you can see, the data line goes low and then the clock line goes low. So here is the device address with this thing, and you can see that it's in write mode. So the initial, when we're writing to the bus to say, here's who we want to talk to, the control byte, it's going to be in write mode. This is the acknowledge. You can see this is a low acknowledge from the slave. Here's a byte. Now this goes along with the protocol of the device. In this case, if I read from address 2, it will give me a 2-byte value, which happens to be the software ID of this thing. So I write that byte, I get an acknowledge back. Now this was connected to an Arduino. So the Arduino inserted an additional stop in here. It doesn't hurt anything because on a read, we're going to do a restart with the device ID in read mode. So that's what's going on there. And finally, here were the data bytes. Now, here's an interesting thing. When there is a read, after a read, the last acknowledge is going to be a NAC, because that says, okay, all of the data has been transmitted. So when we see a NAC, we know that we're done. So you'll see in the code, if you go through and look carefully, the last acknowledge bit is always a NAC, because that tells the external device, okay, we're finished. All right. Okay, slides are done. I know this is a little bit wonky, but it's really simple. Again, we remember there are 4 things that can happen. We have a start, we have a write transaction, a read transaction, and stop. From those elements, you see what they look like here, we can talk to anything. So expect you all have your editors going. And if you will have a look at program 1. Now, fair warning, I am often reorganizing things. So double check, if you left your system set up, double check any new examples that I post to make sure that the pin numbers are match your system, because they might have changed. So I had that, I think came up in the forum, somebody said, hey, I tried to code and it didn't work. It's because I'd moved pins. So always check that. Now, this is a device that a piece of code that I wrote for myself quite a long time ago, and it's become, because you may want to just scan the bus to see what's out there. And so you think, okay, how do we do that? It's actually pretty easy. What we're going to do is we're going to iterate through all of the addresses, and then we're going to send a start and the slave ID, the control byte, to the bus. If the device is there, we'll see an ACK. If the device is not on the bus, we won't get that ACK, and we say, okay, there's nothing at that address, and we can move on to the next. Otherwise, we can log it. So if we run this, oh, I had it earlier, so let me just redo it again. What this is doing is it's going through each of the devices, and it found these 3 things. Now, I skip all bits of the device type clear and all bits set, because they have special meaning and you're not going to see them as general purpose devices. But here I have 3 things sitting on the bus. Now I can tell you, I know that that is the display. I know that that is the EEProm that is on the RTC, and I know that that is the RTC. Now, how do I know that? I went and looked them up. Because there's so many shared things, and I forgot to, one of the things I was going to put in this listing was from a comment in the forum. Somebody had put out a list, I think on the Adafruit site and somewhere else. People have listed the common device types, so you can do that. For those of you that are playing with tacos on your P2, I think Peter has, he has an I2C bus scanner built in for that. And he also has the some ID as well. So, common devices, he'll tell you what it is. Kind of neat. Now, again, because when I first started playing with I2C, I was using EEProms because of the P1, and they always expressed the slave IDs like this. So here's that 4-bit device type, here's the address type, and this X is the read-write bit. So there's 8 bits. It's technically, it's a 7-bit address because we only care about that. Now, if you have done a lot of work with Arduinos, or you do like I did, I took the driver from this that was all written in C, in the Arduino variant of C. One of the things that you have to know is they just use the 7 bits. They leave off the read-write bit. So internally, what goes on in their system is it takes this 7-bit address and it shifts it left to create room for the read-write bit. I just always have a 0 there because that's the write address. So this is a nifty tool. You want to make sure something is there. In fact, that's how I initially discovered problems with this. I wasn't seeing it. And I thought, is it a clock speed problem? Is there some issues? And, you know, investigated, finally hooked up the logic analyzer. So the I2C object, go ahead.
Get removed permanently.
Okay. The I2C object for the P2 has some flexible configurations, and I meant to have that as none. This won't hurt anything that it's set to 15K right now, but I'm going to change it to none. We have to tell it the clock line, the data line. This is the speed, and I have this actually set quite slow, so I'm going to bump that up. And it's in kilohertz. And then this is the pull-up configuration. So this is going to be a very normal thing. And again, I apologize for not catching that before I sent it out to you. So a really standard thing with devices like what we have that already have pull-ups built into them is your clock pin, your data pin. 100 is normally considered as slow I2C, and it's normal I2C speed. And then with external pull-ups, we can turn the pull-ups off. If we look at the code, you can see we have a choice of pull-up options here. 1.5K, there is a current driver in the pin that roughly emulates a 3.3K pull-up and then a 15K pull-up. So that's all configured here. This is, we're not using a smart pin mode, we're just using an enhanced pin mode where we can configure the output drive, excuse me, to either float. So when we say pull up none, anytime we tell the pin to be high, it's actually just disconnecting it completely. It's floating it so that the external pull up can do its job. If we want to use the internal pull-ups, then we set that, and the output driver for the high side of the pin goes through this resistor or has a controlled current source. Now, I'm not going to go through this code. I'll let you do it because it's all in assembly. This is one of the things that is nice about the P2. We can do inline assembly, and you might wonder, well, why did you do that? Couldn't we just write it in spin? And the answer, of course, is yes. The difficulty, believe it or not, with the P2 is it's too fast. The P1, I have a spin version of I2C that works very nicely. Again, Mike Green's initial I2C thing, also spin, works very nicely. The P2, though, is so fast, even with spin, that it's too fast for some devices. By using assembly, I can control the bus speed, and that's why I allow it to be passed over. So this, by passing, you know, kilohertz, so again, 100 kilohertz is a typical bus speed for I2C, then the assembly code can control that, and we never have to worry about it. But you can see, if I look in my summary mode, here's those major transactions. We have start, write. Now, as I told you, this will just do a whole block write, but it's essentially the same code. And read a block, and stop. Those are the functional building blocks of an I2C transaction, and you can use what's in here to then build up any object you want. And we'll see that with the display, because it starts with I2C and then it has the PCF 8574 that is its hardware. That's the little, my LCD is kind of out of the way. If you look on the back of your LCD, there's a chip on there. That's the PCF 8574. So I have a low-level driver just for that, if you wanted to treat it as its normal function as an I/O expander. And then on top of that, we have the LCD code. So you'll see the layers of Propeller objects in this code. Now I have a couple of other things that are useful. So for example, there is this method called present. That's actually what's called by the scanner. And as you see, what it does is the starts a transaction, and then it looks to see if that slave ID generated an ACK, and it will return true or false. So this is a very easy way, if you have a device or you think is on the bus, or you want to verify it's there before you try to talk to it, then present will do that. Now, you can have a slave device be busy. I don't use this very often, but what this will do is it will do the start and it will wait until the device is ready and gives you an ACK back. So it's a way to allow a busy device to finish up, and then you can complete the rest of the transaction. Again, I don't use this very frequently, except as a code shortcut, because most of the time devices are very zippy and you're not going to run into things being bottlenecked. Okay. So did everybody get a display something like this? Or did anybody get a display something like that?
I did. Mine looks
Excellent.
like that because I hooked up my RTC as well.
Say that again, Roy.
And mine looks exactly like yours because I hooked up the RTC.
Oh, good.
As well.
Yeah. Yes, and what forgive me. So on my system, which I don't have a way of showing you, I have in my JonnyMac, I have the RTC module plugged in kind of on the other side of the breadboard. And then I'm using 4 short wires. Now, I think I mentioned this last week. I'm very specific about wire colors that I use. So I have white for clock, yellow for data, red is the 3.3 volts, and black, of course, is ground. So I have those 0 and 1 are my clock and data, and then I'm getting power. So I'm taking jumper wires from the female connectors over to the breadboard in front of the clock. Now I put female wires onto my LCD, and those are going to the male pin headers. Now the LCD is powered by 5 volts. This is not going to create a conflict because the power for the 5 volts is going to the guts of the LCD, and we have pull-ups. So between the propeller and that 5 volts, we have 10K pull-ups. So everything's fine. It's not going to hurt anything. So all of these things are connected on together, even though they don't physically look like they're together. Electrically, they're all the same. And for those of you that are using ANSI terminals, I tried to make it a little fancy by coloring things a little bit, made it a little nicer. Okay, so that shows us we have stuff. Any general questions on looking for I2C? Again, remember, to look for a device, we're going to do a start, and then we're going to write its slave ID and look for an ACK. If we don't get the ACK, we know the device isn't there. Now, just looking at this code, so you can see what I'm doing, I have 2 loops, one inside the other. So this loop, this outer loop, is I have a variable called type, and it's iterating through those 4-bit types. I'm going 1 to E, and this is printing it. Then this is going through the possible addresses, which is 0 to 7. And so device ID, this dev ID, this takes the type and the address with some shifting and puts it together into a control byte. And there you can see it. It says if I2C.present for that device ID, then we're going to write it down. And I also save it into I have an array of addresses. Now, I don't expect I'm going to have more than 32 I2C devices hooked up to my Propeller at any given time. So I limited it there. If you're going to go crazy, make that number bigger so that you can save them all, not clobber your memory. Because that's what, in the end, when we finish up, it's that saved array is what reprints this down here. So this all kind of prints on the fly and saves what we found. And then this just reprints what we found in both styles. So you can see, wide open what you're looking at. Okay. So I have used this many times in projects. It's a very simple program, and it makes things super clear. I hope you find it useful too. Okay, I know everybody's jonesing to play with the LCD because they're super useful. So let's do that. This one, the PST stuff is included in the code, but it doesn't actually is not used in the program. So just, if you press F10, you should see a cheeky message scroll across your LCD, and then you should see another message be revealed by a chomping Pac-Man character. So, what do you know? Everybody get that?
Yep, I got it.
Okay. I almost started saying Bueller. The movies knew what I meant by that. All right. So if you look up in the compilation window, now you can look at mine. Some compilers won't show you this, but if you look, so we have this object called JM LCD PCF 8574. There are other I/O devices for I2C that are used in LCDs. This one is the most common, but there is another one called the MCP 3208 that is occasionally used in LCDs. So you have to be mindful of that. But you'll see here, look at the layers. So here's the I2C object, or sorry, the LCD object. Here's the code just for that chip, the 8574. It's a generic I/O device. In fact, if you look, it's very simple. There's not a lot to it. You can write to it or you can read from it because it's just an 8-bit device. So that's all you can do with the PCF 8574. But that needs I2C to do all that stuff. So you can see how things are built up. Here's our application, and we're going 3 layers deep to build the object. But that's the power of this kind of programming style, is that these 2 things can be used in lots of places. Especially this one. This, you know, you'll use it a lot, or I use it a lot. I have dozens and dozens of I2C based objects. So let's go ahead and look at the demo. Now, it gets a little hairy talking about I2C about LCD initialization, so I won't go into that, but suffice it to say that there are rules for sending signals to LCDs, and the tricky bit of doing it through the PCF 8574 is that we only have how do I say this? We have there is a point in talking with an LCD where you have to put data on its bus and then blip a line. Well, now we're doing that through I2C, which means we have to write all the bits with the data set up and that line low. We write it again with that line high, and then we write it again with that line low. So I will tell you, doing an LCD over I2C is slow, you know, compared to direct connection. But again, it's very convenient. And the nice thing is this, you know, we have this 2x16 display, but you can get, you know, bigger displays that work with the exact same code. So just be mindful, it does take a little bit of time. You may never notice it, especially with the Propeller 2, but there's a lot of stuff going on under the hood because of the way the LCD wants its data, which is a parallel bus. So we're doing the serial bus to a parallel bus and mixing it all together. The start for the LCD is going to be very much like an I2C thing, because it is. We do need to know the address of the device, and that's where this comes in handy. Now, when you're trying to figure out what an individual device is, disconnect everything else and just look at that device, and you'll see the code. In this case, I know that it's 4E. So this is the way my I2C, oh, let's go, sorry, I want to go to this level. In my generic I2C objects for parts, and there's a gajillion of these parts too, I always set up my addresses. Now it turns out the 8574 has 2 variants. A normal one and an A one have slightly different types. So my code has the ability, because otherwise, I mean, that's the only difference. So I have a start and a start A that knows how to deal with that. And then all the rest of the transactions are the same. So for this, again, it looks very much like a normal I2C setup, which is other than we've added a device address that we save in here. And the address in this case is going to be that 3-bit value. And you'll see that right here, the device ID is synthesized based on the device type we're using, and then the address bit, which we shift over by 1 because we need space for the read-write bit. And then in this case, my start will send back true if we have the device, because you see that the I2C bus has been set up. And now we create a device ID, and then we say, hey, is that thing sitting on the bus? So this is the PCF8574 object, or I will suggest it might be a good template if you're interested in finding other devices, generic I2C devices. You'll find that almost all of my I2C creations look a lot like this. And it will just, the details will get into what they can do. As I said, there's only 2 things the 8574 can do. You can either write to it or you can read back from it. That's it. Other devices will be more complex. So in the LCD, if you've played with any other LCDs, a lot of this will look very common. In fact, these constants are from other LCD programs that I've written that you may have seen. And after we get it started, then the I2C aspect goes away. That's just the communications. It's been abstracted away. So now everything is just general purpose communication. So we can clear the display, we can move the cursor home, just really generic kind of things that you would have for a display. So you can see I have lots of things that I've used over the years. I've done a lot more numeric formatting lately, so those things are in there. Now you'll notice, and we talked about this in week 1 and a little bit last week, I have private methods here. These are things that only this object needs to do. We don't want the parent coming and trying to run these things, because this is doing the configuration for the LCD. We won't go into details, but if you look at the specification for like the HT44780, which is the driver for the LCD, this will all make sense. I'm following those rules to configure it. I just have to do it through this 4-bit interface, versus normally we'd have a 6 or a 10-bit interface, depending on how we were treating the bus. So here's where I was talking about where we have to do 3 writes to the bus in order to do that blip action. Okay. Any questions on the LCD? It's really kind of easy, and it's nice and useful, and you can do, all the normal things that you would want with it. I'll show you, in another detail. I'm going to put some additional diagrams into the presentation. So if you down that later, you'll have that. One of the things that I love to do is custom characters. So when that little Pac-Man guy is on the screen, those are not characters that are built into the display. I put them there. That little goofy smiley face is too. And Ken and I were talking earlier, and it dawned on me, this code and this here, and this demo code, I wrote in 1994 for the basic stamp 1. So I've been doing the same demonstration for LCDs for a long, long time, because it shows off all the kinds of functionality. In the LCD, you have the normal ASCII character set. The LCDs often have extended characters too, from character number 128 up to 255. But normally in the ASCII set, characters 0 to 31 are control characters, and we don't mess with them. In the LCDs, characters 0 through 7 are custom. So there's RAM in there that we can customize. And so this map defines the custom character. And so this is the top line the next line, and then this is the bottom line. You notice the bottom line, I always leave it 0 because that's where we might want a cursor if we're doing cursor stuff, and you'll see that in a minute. So if you drew this out, well, here I will. So comma, so 0E is we'll do dots and X's. So that would be dot 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 dot, and then E is XXX dot, right? And then this would be, I'm only going to do a couple of lines. Same thing. This would be dot, 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 X, 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 X. And so you'll start to see that as we go down, this is going to create, if I did a couple more, this would create the open mouth character. Now, the LCD characters are only 5 bits wide, sorry, 5 bits wide. So these 3 bits are not used, but it's better just to 0 them out, okay? And I have in the past done, used binary numbers to create character maps, but it gets a little tedious, and so I don't. One of the things that I was thinking about is that a long time ago, I wrote a little program called LCD Character Creator. It was when I was working at Parallax, and I can dig that up somewhere. But what I found out yesterday playing with processing is you can actually export it to an executable file. And so I thought, man, maybe I will try to do that and then have it send the data to the Propeller. But the custom characters give you the opportunity to make really neat applications. In fact, I'm going to go back to this dude. Remember this giant thing? This was an industrial controller for HVAC, and it had a big box that this was mounted in, and all of the wire races and all of that. And they had a 4x20 LCD. Inside the system are 16 configuration registers that can be in 3 states. And they wanted a way to show that very quickly. Well, I created 3 custom characters that look like a switch in a neutral position, in an on position, and an off position. And then I was able to put along the bottom of the LCD those things, and they could see it in one snapshot view. And the customer turned to be very, very happy about that. And it all came about using, a simple, inexpensive, off-the-shelf LCD. Now, in that particular system, there's RS-45 on this board, so we could talk to a big industrial HMI. But if they had somebody on site in the field, that gave them information that was really important.
I have this demo spooled up if people want to see a video of it.
Oh yeah, please.
Okay.
Yeah, thank you.
Take just a minute. Here it is.
One of the again, so we only are using a couple of wires so that's nice. The one thing about that though is we have no way to control the brightness of the backlight, just that it's on or off. If you're doing a traditional LCD connection to the P2, which I'm going to write some code for in a couple of weeks, you can use a smart pin in PWM mode to control that brightness, which would be really nice.
Okay, back to you.
Okay, thank you. Okay.
Unfortunately, I joined the club of Mike Green and Carol Hazlitt, and my P2 Edge was detonated today.
Oh, no.
Yeah.
That's not a good thing. Stop it. Okay, let's go to program number 3. And I just saw on the screen when we do that, I saw Francis Bauer, and I wrote this program because of something he posted in the forums. He very kindly posted a character map of the, for this LCD. But I thought, well, we can just use the LCD to do that. Now, sorry, this also requires the rotary encoder. We're trying to bring in components we've used in the past. So I'll talk about it while you're hooking that up. Now the connections are in the code. Again, check to see what I've got, where I've got them. If you have the LCD already working, there's no change there. The encoder A pin is on pin 8. The encoder B pin is, and the encoder button, which is not used in this demo, is on pin 10. Now, if you already have your encoder hooked up somewhere else, just change your, just change those constants. That's the way we do things. Now, while people are doing that, did anybody take up my challenge last week of figuring out how to make the rotary encoder roll over or roll under? You did? Excellent.
I did.
All right. So here's how I do it. In this particular case, we have a byte which can go from 0 to 255. So what I'm going to do is I'm going to expand my encoder limits by 1 on either end. So I have -1 on the low end and I have 256 on the high end. Right now, when you run this code, hopefully Ken will be able to run it so other people can see what's happening. What it shows, it says C-code, which is for character code on the top line of the LCD. And then I have the code in both decimal and hex. So those aren't two different things. It's just the same thing in two different formats. And then on the bottom line, it's the only thing on the line, is the actual physical character. Now, when you turn your rotary encoder, you can go through the characters. In fact, if you run this after the little chomping demo, you'll see those characters are still in RAM because we didn't power down the LCD. I'll wait a second because I know that people are working along trying to get their stuff hooked up. But, or Ken, if you can get it hooked up so everybody can see it.
Yep, I'm still wiring.
Okay, I really need to get a camera so I can start showing people these things.
And you said the clock is
for the encoder?
Yeah, the
encoder is on pin, the clock pin is on 8, the data pin is on 9, and the button pin is on 10. And then of course, ground and 3.3 volts.
I got it working. I reassigned the pins back to what they were in the previous demos,
okay,
which was 18, 16, 17.
Yeah, they were scooched over a little bit. Yeah.
Because that's where I had it plugged in already. So I just
yeah, exactly. And that was the point. And so thank you for saying it. So there's two ways to go. You can move your wires or you can move the assignments. Now, if you have a piece of hardware that's physically built, in this case, Roy could have moved his things, but if you have a board, you just move the assignments. And that's why we do these named constants, so we can change things very quickly.
It's cool. You can see all the little custom characters at the beginning.
Yeah.
Yeah,
you'll see
this,
some.
John?
Hmm?
You want me to share
please,
the
Ken.
display? Okay.
Yeah, and then we'll talk through it. Yeah, this is a really simple program, but also, again, very useful. So there you go. So character 32, as many programmers know, is the space. So that's why we don't see anything on the screen. Now turn clockwise, Ken. So there's ASCII 33. So as Ken goes through, you can see in the bottom line, the left column, you'll see the actual character. Now, the ASCII characters, okay, we already know, but once he gets up out of the ASCII set, so keep going, Ken, you can zip it up. It'll go pretty quickly. Now you can see the other characters, the non-ASCII characters that are built into the display. There's a lot of foreign language characters. There's and other kind of specialty characters. Now there is an interesting aspect to this code. So go ahead and go to 250, go, when you get to 255, go slowly and continue going clockwise. 255 is going to be just a big block. Okay, now go click again clockwise. Now we've rolled over to 0. And the way that we do that in the code is we look at the encoder value. If it's 256, the only way to have gotten there at 256 is to have gone from 255 to 256. And so the code will say, oh, we have a rollover. We reset the encoder to 0 and use that. Now there's another specialty case, because in the LCD, we have this block of 7 characters, and then we have a gap of control characters that are not displayable, and then we have the ASCII set. So as Ken goes through slowly, so here's the chomper characters from the demo. Now after that, you'll see noise and who knows what's in there. Like mine has lines there. So you see Ken's is a little different. Now notice that from character code 7, which is the last of the custom things. Now if Ken turns clockwise, it jumps, well, that was a little skip in the encoder, but if you back up to 32, so it will jump between 7 and 32 back and forth, and that's built into a bit of conditional coding in the program that you can look at. So this is really simplistic, but it's a little mini HMI, and sometimes you have to think about these kind of things and then write the code for them. But this is what we're doing all the time when we're making industrial kind of devices.
It's a super demo.
Yeah, I have often just before having encoders laying around all the time, I would always just go slowly, and then I would stop the program and say, okay, that's the character I'm looking for, or that's the thing. And you could certainly, I expect people will enhance the code. You could maybe have a group of characters where the center one is what you're changing, so everything else is aligned with that, so you can kind of see what things look next to each other. But yeah, so now if you get another type of LCD, run it through, because again, the upper set from 128 to 255, that's not really defined, and so the manufacturer is going to do their own thing in there, and you might find something different in another LCD. Yeah, can I go back, Ken, so we can look at the code?
Yep, here you are.
Okay. All right, so the code is really simple. Here we're starting everything. So that as always, I have the value that I'm dealing with, and then I have kind of a, hey, did I change value? And I always call mine last. So I'm pre-initializing them here. Since I start at 0, we're clearing the encoder, which sets it to 0. And then we've set the character code to 0, and then last to -1. The reason I do that in the beginning is that the first time through, then it will force the LCD to be updated. Okay, so that we always get an update at the beginning. And so this is very simple. It's homing the character, it's printing that string. This is, JDEC is justified decimal, so I'm doing the character code. This 0 means use as many digits as you need, but in a field 3 characters wide, and pad the front end with spaces. And then here, a little separator. Remember, I'm showing the ASCII version, the hex version of that. Doing that in 2 characters, moving down to line 1, and then just doing the, printing the character, and then saving what the last was. Now you can see it's a very tiny bit of code that is handling this rollover and roll under situation based on how we set up the encoder. Because remember, the encoder can go to -1 and up to 256. And this is what allows us to do that. So these are not in any particular order, but if we're going through forward, when we hit character 8, which is just past the custom character set, we want to reset to 32, which is ASCII space. Now we can roll all the way through the ASCII set and the extended ASCII set. And if the encoder hits 256, we know we've gone past the ASCII, so we reset the encoder to 0. So we've wrapped it around back to 0. Now, if we're going the other way and we hit -1, then we wrap the other way and we reset the encoder to 255. And likewise, if we're on 32 and we go back to 31, then we jump over to the last character in the custom character set. So you can see it's a very simple bit of code, but it creates a very nice interface. And that's one of the joys of programming, is finding these little recipes like this that can make the user experience very nice. That was when I was a product manager at Toro, that was a very big part of my job, is the user experience with, you know, the controller products. So I didn't do the electronics engineering on the inside. I did the product design and how people interacted with it. Part of my job was, I often worked with the group that did our publication stuff. We would create a user manual before engineers started designing circuits or code, because we wanted them to understand the human aspect of the user interface too, because it would affect their internal designs. But this is cheeky, but I quite like this, and we'll use it, this kind of thing, more often. So it's taking advantage of two things. It's the setting these out of bounds numbers on the encoder to act as flags, and then a little tiny bit of code. And you see, here's where the case statement makes this really, really easy. Any questions on this, dude? Okay. Hope you have your Christmas lights hooked up, because now we get to have some more fun. Now we get 3 pieces of the puzzle that we've been dealing with. So if not, yeah, we'll just give a little time. Again, my situation, I use the same as last week, I think. I have my pixels connected to pin 48. Oh, and forgive me, I'm using a ring. So I probably left the driver start method to WS2812B. So for the Christmas strings, you'll want to go down to the setup method. And if you're using the other string, pardon me, change that 2B to a 1, so that you get the WS2811. Because remember, the 2811 and the 2812, the 2812 swaps red and green, the 2811 doesn't. So your red and green will be out of whack if you have one and you're telling it it's the other. So this is the proper setup for the Christmas lights. If you're using a ring like I have, or I don't know how many you saw it, Roy made this really cool little Christmas tree thing with a bunch of rings, concentric rings that are stacked together. It was really nice. Lots of fun animation in that. So those are 2812Bs.
Yeah, I first ran it with 2811 set, and all the colors were whack.
Yeah.
So I found the line and fixed it, and it worked great.
Yeah. Yeah, it's an interesting thing, because, you know, the 2811s are just generic PWM drivers, and so they don't assign anything to it, because they're just their external chips. When the 2812s and then the 2812Bs came along, they put the driver inside the pixel, so they pre-wired everything. Yeah. It just happens that the people that are building RGB elements out of WS2811s use the first channel is red, the second channel is green, the third channel is blue, like you would expect. It is a little odd that the WS2812 reverses red and green, but it probably has something to do with the internal layout of the die. If you look very closely at the pixels, you can see everything is all on a piece of silicon there. Oh, jumping Jiminy, did I leave a mess? I'm so, you know, I'm so crazy about, so if you've got ragged stuff here, then it's my fault, forgive me. God, I hate that when I do that. Now, this is a fun thing. hopefully Ken will be able to set it up so he can show it, but I'll start talking about it. Now, one of the things, this was kind of inspired by, I was watching Kevin's video on YouTube from last week, and right off the bat, he used the encoder to kind of move around the LED. And the funny thing is, he actually kind of, had an off-the-cuff comment. He said, yeah, I don't think this is really that useful, but I just did it. But I'm here to tell you, Kevin, that kind of thing is useful. And one of the things that I'm going to say to everybody is that a big part of an engineer's job is creating one's own tools. And I'll show you a real world thing. Hopefully I still have it. Oh, darn it. Did I get rid of that? All right, hang on. I need it. When some years ago, I was doing electronics, and still do from time to time, for my friend Steve Wang, and we created a costume for Wes Borland, who is the guitar player for Limp Bizkit. And let's just be easier to see. Did it? Oh. This costume actually has old school WS2811 pixel strips on them. I didn't make the helmet nor these gauntlet pieces. They asked me to program them. The trouble is that they wanted, it may be tricky to see through the screen, but there's a bright stripe there and a bright stripe there. What they wanted was these two stripes to kind of go over his head and down his arm. But you can see, if you look, I'll zoom in, you can see the orientation of the pixel strips don't match the orientation of the stripes that they wanted. In fact, they're 90 degrees out of whack. And the helmet is very oddly shaped, so there was lots of other funky stuff in there. So this was about a 24-hour no-sleep project. What I ended up doing is I had all of this on the bench in Steve's shop, and he and I are very late night guys. That sometimes, if people were sleeping on the floor and he's sculpting a creature from the Black Lagoon for another project, and I'm doing this, and we're, sending barbs at each other. But what I ended up doing is taking the costume and laying out painter tape, one of my favorite tools, across the helmet and down the things, and defining where these pixels are. And just like where Kevin had used the encoder to move around LEDs, I was doing it with the keyboard. What I would do is I would move and select LEDs, and then I would press the space bar to turn it on. And I would turn on all of the LEDs that were within a virtual stripe, and then I would write them down. And so I had to go through the whole thing, and I created these groups of discrete pixels that became virtual stripes. So then later, when I wrote the animation code, I could animate them doing the swoopy kind of thing. And so this is something that for those of you that are new to coding, or a reminder for those of us that are old timers, writing code that is not going to be publicly used happens all the time. We're always writing little test bits to prove things and make our own life useful. So that's where this next project is, because I, again, working here in Hollywood, I'm dealing with artists all the time. They'll often say, can you make that a little more red? Well, how much is a little more red? It's hard to see, especially with lighting stuff. So the idea behind this program is that we can, using the, we're using the LCD and our pixels, you can see I've got some lit up. What we're able to do when you bring up, oh, I better run this program.
Does anybody have that working so they could share screen? I'm using the P2 eval board and would need an external power supply.
Oh, yeah, you don't have enough power, do you?
Right.
Well, you know what, Ken? Do you have the ability to hook it up? Because this is only running 5 LEDs, so you can get enough power out of it.
That's what Roy said. My COM port 8 download looks frozen for some reason. Give me a few minutes.
So if you run this, when you run this, not if, when you run this, the top line will say channel, and it will go through. Now, I only allow, because of these current limitations, only 5 LEDs. Yeah, you can set that here, there is a constant that is called channel max. That means there's only 5 channels that we can modify.
You're also only setting the values to very small numbers, so the LEDs
Yes.
don't get very bright and draw a lot of power at all.
Right, and that's a good point. Yeah, you have control. Now this will let you set them all the way up. That's why I did this. But normally you don't have to see a whole bunch of things. It'll actually start to affect your eyes. So a few pixels will show you the color. But what what you'd see on the screen is the channel number on the top line, and then the bottom line is a hex value with underscores between the constituent elements of the RGBW value. Now, again, with the WS2811 and the WS2812, we only have R, G, and B, but this program will work with other devices too. You just have to set up the start command. So if you wanted to throw the white mix in there, this will. So if you look carefully at the display, you'll see when it initially starts, there is an underline under the low digit of the red channel. And if you turn the encoder, you'll see that value go up in the display, and you should see your first, oh, there we go.
Sort of.
Yeah.
See if I can kind of get it all in the same. Is that good enough?
Yeah.
Okay. Oh,
Yeah, so if you turn your encoder, you should, well, you've already got it red. So you can see on Ken's display, the red channel is set to 9. And as he manipulates that channel, then the LED changes live in real time. In fact, oh, so this, well, you would have had a compile problem if you didn't get this, because I added 2 features to the driver so that we could manipulate individual bytes by an index, just so we could do this. So in fact, you know, I will suggest each week there is that library folder that comes over with my zip. Just copy everything from there into your Propeller library so you have all the latest. So now just do a quick click on the encoder, Ken.
I knew you were going to ask me for that. I have to wire the button.
Oh, doggone it.
Sorry.
Yeah,
which
this
pin?
one does use the button. That goes to pin 10.
Okay.
Yeah, we got to get to the other elements.
Yeah, you need short press and long press to be able to control everything.
And we have that in this code.
Yeah, I've been playing with it. That's why I said that.
Hey, John.
Yes, sir.
Yeah, I have. I'm running this with FlexProp, and it won't compile. It doesn't like get MS. It doesn't like the get millisecond.
Oh.
But funny though, I actually did a terminal search through FlexProp, and it looks like Flex Spin actually knows get MS.
Yeah, so that's a thing to talk to Eric. I thought he had put it in.
Maybe it needs an underscore or something for this. I don't know.
I don't know. I know that is a thing, you know, it's obviously a spin thing. It's something I fought for. Chip put it in, took it out, and I fought to have him put it in just for this. You could use just the count register, Dennis, and then, you know, take the result of the subtraction and divide it by ms_001, and that'll get you back to milliseconds.
Right. Okay. But maybe he has an underscore in front of it for right now. I know some of them he did.
So you'll notice now, just do a quick click down on the button, Ken. And what you see, if you look carefully, is the underscore moved under the green channel. So if Ken starts turning the encoder clockwise, that's going to get yellowish, that LED, and move towards green.
Yep.
And so let's say you decided that's the color I want. Now you want to move to channel 1. So what I want you to do is press the button and hold it for a full second and then let it go. Now you see the channel changed. So this is one of those kind of programming trickery things we sometimes have to think about. We sometimes are given hardware that we can't control. In this case, we have one button and we want to do 2 different kind of selections. We want to move from field to field, or we want to move to another channel. So the way that we're doing this is we're checking to see if the button is pressed at all. And if it is, we're measuring how long it stays pressed. So we have a definition for a short click, which lets us go element to element within the same channel. And then the long click, which lets us move to the next channel. I actually quite like this too. I know I'll be able to put this to use in a couple of projects.
So John, for users that are doing flex prop, just put an underscore in front of get MS. It's here.
Okay.
Yeah, it works.
Thank you. I'm sorry I didn't have time to test with FlexProp today. I apologize to the group. I normally do that, and I didn't have a chance today. Forgive me, please. Now you'll notice that Ken made a change to the white byte on this, but it will have no effect because there is no white fourth channel on that LED. So this is the kind of tool that I would use with a client who wants to figure out what color is going to look best. And then we can actually tweak it and say, okay, there it is. And we're doing it live. So again, this is another little tool that I wrote for, again, it was, part of our training, but the inspiration came from what Kevin was doing and what I'd done in the past and my dealings in the past. And, again, in our industry, it's very artistic. So I can tell a story kind of related to that. If any of you have seen that show, The Mandalorian, interestingly, the backgrounds are primarily digital. They shoot on a big digital stage, but that digital stuff is not just 3D rendered, it's rendered live through a game engine. And our friend Rick, who many of you know, the Propeller minigun guy, he works on the show, and he said it was crazy. He was watching them one day where they had a street scene, and one of the directors said, "Hey, turn up that street light." So there's a big bank of computers in the back of the room, and a guy adjusted it, and the animation, it changed in real time. So, the having tools or being able to build tools to do this kind of stuff is very, very useful. And this, again, now here with an LCD and a single encoder, you have the tools to build a nifty little user interface for a huge variety of devices. Okay. Can I go back to the code, Ken? So we can.
Just having so much fun playing with this.
I really like this program, if I do say so myself. Yeah, I was sweating a bit. I thought, oh man, am I going to be able to pull this off? But I do like this program. So we'll go through and see what's happening. Now there is a, I pulled things a little bit apart. I try to keep my main loop fairly simple. So in this case, it's the same kind of thing. We're looking at the encoder, and if the value changed, then what we're going to do is we're going to update the LED that we're pointing to. So there's a channel number and there's a color index. So the color index is the byte within that long. So red is byte 3, green is byte 2, blue is byte 1, and white, again, not used here, is byte 0. So that's what color index is. So this is my actual pixel channel. This is the color index for the red, green, blue, white element. And what I'm going to do is I'm going to set it to whatever the current position of the encoder is. And since there was a change, then I need to go update the LCD. And since this is a little bit of stuff, I just separated it out into its own kind of module, which means later, if I wanted to move this onto an OLED, then all I have to do is change this code. The main loop, stays pretty much the same. So here, really simple stuff where here I'm starting by disabling the cursor. Again, this is just my aesthetics. If you try to write to the LCD while the cursor is turned on, you can see it, and it just makes me nutty. I don't like that. So I start by turning the cursor off, and then, we home the cursor and write the channel, and the channel number is a decimal. And now we move down to line 1. Here we're outputting the constituent bytes with a little underscore. I originally had it just 8, characters there as a hex value, but it was a little noisy to read. And since I have in my other listings, I put the underscore to separate out the color elements. I just thought, well, there's room on the LCD. Let's do it that way. Now, I didn't want to goof around figuring out, a little math equation to position the cursor based on where it was. So I just used a little lookup. So this is the underlined column. I just wrote it down. I figured out when I'm red, which is, when I'm in the white column, that's actually byte 0 of the elements. So that's at position 11. This is the blue, green, and red. That just made it really easy. And so down here, you can see when I want to turn the cursor back on, I look at the color index. This will move the cursor to the correct column, and then I turn it back on. So what you see is a very neat and tidy display. You've all heard my, maniacal stories about how I want to keep my code neat and tidy. Again, user interfaces and those kind of things, I try to do the same thing. And it's just 2 lines of code to turn the cursor off and then turn it back on. It's not a problem. And it just makes things look more professional and more presentable. So the other nifty bit, which I've done in the past. So just for those that missed it. So if you're using flex prop, you need to do this. Is that right, Dennis? Put the underscore in front of get MS?
That is correct.
Okay. And I'll have to figure that out. Don't know if I can, well, that's just a note we'll have to have. I'll put in my code. If you're compiling with flex prop, you may need to change that because I don't, there's no conditional debugs or conditional compilation within Propeller tool that I could use to change that. All right, so then, but this routine is what tells me I had a button press and what kind of button press it was. And it's really, really simple. When we come to the routine, we're gonna call it, and this debalance is a minimum time that we want the button to be pressed before we acknowledge that it actually is pressed. Now, these encoders are really stiff, so if you make them click, they always pass. But now it's just the distance. But if you're doing, a little button on a, breadboard, one of those little type of buttons, that minimum debounce period will be useful. So when we come in, we look to see if it's pressed at all. If it is, we're going to take a snapshot of the milliseconds counter that is in the spin interpreter. Now we're just going to wait until the button is released. When that happens, then we're going to grab the count that's in the milliseconds timer now and subtract the original count from it. This now is the duration that the button was pressed while we were monitoring it, because you could have pressed the button beforehand. But in order for this to operate, you have to release it. You can't be holding the button. You're not going to see anything change until you release the button. And then just a last qualification thing here is if the time was less than our debounce requirement, then we just set it to 0 and we move on. So a 0 back, it acts like it wasn't pressed at all, and it's easy on the other code. So here in the program, check is going to grab the button press timing. And now when you're doing these things with a short and a long press, you want to check the long one first, because if it's a long press and you check this one first, this would work, but this one is also true. So check the long first and then check the short. So if it is a long press, we increment the channel and then compare it to the maximum count. If that hits there, then we just wrap around to 0. And if the, since we know there was a change, then we're going to reset the encoder to the color that was in that LED chip for that channel. So this is one of the new features I added today. It's called Get Level. And what it is doing is, it is grabbing the color byte for this element. Again, red is 3, green is 2, blue is 1, white on those type pixels is 0 from this channel. So it's reading an individual byte value from the pixel. What I was originally going to do is just grab another way to do it with 2 lines of code, I guess, is to grab the full RGB value out of the buffer and then do the dot byte. That's another way to do it. But I thought, well, this is useful enough. I'm just going to make it a routine. So there is get level and set level are new features of the driver to adjust an individual color byte with a value and an index. So here's a long press. We'll just move to the next channel. If it's a short press, then we're changing the color index. Now in this case, we're going 4, 3, 2, 1, 0. So we subtract first, and if it fell below 0, this is where, you know, I actually ran into a problem, and it was easier to define this as a long. Both of these don't need to be longs. They could be bytes, but by having them as signed values, it just made the rest of the code easier. So again, you know, sometimes we have to think through these things when we see odd things happening. It's easier to waste, but you know, I'm using a couple of extra bytes for the variable just to simplify this code here, and it's consistent with the way it works. This is a common mechanism that I use a lot. And this plus or minus, comparing it to a value and resetting. I guess it could have also used a ternary operator, but I think this is a little more clear in this case. So in either case, if there's an adjustment, we update the strip and then we update the LCD. So simple code, but again, I think this is useful, and I know I'll put it to use for some of my Hollywood projects. In fact, I've got 2 friends in the business that I'm going to send this to today because I know that they'll use it too. They're always having to adjust colors, and that's the hard part. You know, people come along and say, yeah, it's a little too green. Can you fix that? Well, unless they can see it, it's tricky. Any questions on this program? Again, maybe I'm just, because I'm a little punchy, I've had a really busy week. I think this is a useful bit of code, and I'm quite happy with this program. Okay, if everybody's happy with this, we'll move on to some less glamorous stuff, but useful nonetheless. The next program is called, it's for the DS3231. This is a real-time clock. And I'll just run mine. Let's see. And not a lot going on here, just showing me the temperature in my office and the current time, which does match. I set this earlier so that the time was correct. So that is the current time in California. Now, RTCs are pretty easy. We won't get into a gigantic amount of detail, except to say that RTCs use binary coded decimal values. They don't tend to use decimal values. So all of these registers, well, and here I can easier show you in my code. So in this application, which is just talking to the clock so we can prove that it's working, you'll notice here I've commented this out for the time being. It says initialize RTC. If I uncomment that, what I can do is I can go down here and I can set up these registers, and then in my office I have a monitor with a clock on it right here. So what I do is I set it for a minute or so ahead, and I wait for the second to hit 0, and then I press the button and then get it to synchronize. But you'll notice these look like hex values, but you can see now this doesn't match. This was 29. When I set this, I set it at 2:29 this afternoon, and you can see 1400 hours. This is, you notice the order here is seconds, minutes is hour. 1400 hours, or 14 in 24-hour clock, that's 2 o'clock. So this looks decimal here, but we're doing it as hex. So binary coded decimal is a system that uses, again, it's kind of a hex function, but we only use the digits 0 to 9 in each nibble. And again, real-time clocks use this quite a lot. So you have to contend with that. Now, inside the object, there is a couple of conversion routines that will take care of converting between. So this one, BCD to DEC, will take the BCD and it will convert it to decimal. And you can see here was the original spin code. And just as an exercise, I converted it to inline assembly. But what you're going to do is you're going to take the upper nibble of the BCD byte and you're going to multiply that by 10. And then you're going to add the lower nibble to it. So this shifting is just doing isolation. So upper nibble times 10 plus the lower nibble. That's going from BCD to decimal. Going the other way, we take the decimal value and divide it by 10 so we can get the 10's digits, and then we shift it left by 4 bits to put it into the upper nibble, and then we take the remainder of dividing by 10, and that becomes our 1's digit. So very easy. And again, this was with inline code, it makes it a little bit faster. So the real-time clock chip now has, remember on the PCF 8574, there was not a lot of things going on. You could just, write to it or read from it. With the real-time clock, there is a bunch of registers internally. So they're all named here. And these will match the documentation. One of the things that I should say, you've now got 3 I2C parts, if you never had any before that you're using. Please go to the internet, since you know how to do that, and download the data sheet and just have a look through. You'll see, looking through the data sheet, oh, that's what that is. That's what it is. Always, whenever you get a new part, the first thing you should do is download the data sheet and save it on your computer. I have a folder called Tech Docs. Anytime I get a new part, I immediately get the data sheet and stick it there so that I have it even if I'm offline. So these are the various registers. We saw this earlier, how I do the read and write things for the device ID. You'll notice that again, in real-time clocks, we don't expect to have 8 real-time clocks hanging on the same bus. And so we don't. So we're always going to have a 0 address. We start there, but you'll notice with the clock, when we're starting the real-time clock, there's no address for it. It's just the device. We don't have to tell it clock number 1, clock number 2, because there isn't. There's just one clock. Otherwise, we're using the same things. And here's a good example of, remember that I2C transaction stuff that I showed you earlier. Here it is in actual practice in a part. So we're doing the start. We're doing the write with the device ID in write mode. Then now you have to get this from the documentation. The next thing to do is what register you want to write to. So it's the address that you want to write. And in this particular case, most I2C devices will do sequential reads and writes for you. So what that means is at this point, the RTC has set its internal address pointer to the seconds register. So the next write is the seconds. Now the internal address register advances to minutes. So I can write minutes and then I can write hours because the sequential writes are built into the I2C. So it makes it really nice. You can read and write a block very simply like this. I'm spelling it all out because remember every parameter that we pass in spin is a 4-byte long, but these are bytes. So it just made it easier to do it kind of individually like this instead of trying to reorganize things and do it as a block. And then finally, remember, we end the transaction with a stop. So there is, going back an hour and a half or so ago, we saw all that mishmash going on creating an I2C transaction, there's how simple it is to code. It's really easy. And once you start going through I2C docs and looking at parts, you'll be able to put together anything. It's really, really very simple. And I encourage you to, between now and next week or sometime, go find an I2C part that nobody's written a driver for, or even if they have, write your own. Try to do this because it is simple. So here's, you know, another thing, different set of registers, same kind of thing. Now, in this case, we're doing a block writes. So we're passing a pointer to the block of bytes we want to write. But you see it, here we are, there's a start, there's our slave ID. This is the register. We need to pass the beginning register to write to. And then this number N is how many of those bytes we want to write. So that's why we have this, we have a repeat loop, and then we just write, we're grabbing a byte from this pointer and then incrementing the pointer. It obviously is being written. Once all that is done, we do a stop. So that simply, we've just blasted out a block of data to the I2C device. And in fact, I'm using this as a kind of my fundamental writing thing here where it says write register. Notice I'm calling write and I'm saying just write 1 byte. And here's my register that this is coming, this and this are the same. And the pointer is to whatever was passed over there. So I'm pointing at this parameter, and then this code is writing that. So this makes it really easy. So here's, for time, I know I need 3 bytes. So in this particular case, I'm gonna have 3 bytes stored in my application somewhere, and I'm gonna tell it, write 3, start at the seconds, there's the address of my bytes in my application. And you can see that if we look in the demo, I did. So I have a method in there called, RTC time. What's happening, I have these bytes here. So these are arrays, which I can treat as a block. So here's the read time, which also requires a pointer. So if we go back and look at, oh, sorry, the read works similarly. Here's the block read. Again, now this is a little more involved. As you saw in the I2C transactions, we have a start, we do the write, then we're going to write the register, and now we have a restart. And you'll remember in that slide, it was this one here. This is a read diagram. So we send the control byte initially with the read-write bit set to write. Now we're sending an address, and then here's that second start. This is called a restart. And you'll see this whenever we do a read, we have to initially send the slave ID and what address we want to start with. This is an EEProm, so it's got 2 bytes, but it doesn't matter. So it's control byte and address, however it wants that set up. Then we do a restart and we send the control byte again, but this time the read-write bit is set to 1, which is telling the slave we want to read bytes now. So what that will happen is the next 8 clocks, the slave is manipulating the data pin, and the master is reading them back in. And now what the master will do is it will then send an ACNAC to the slave device. So either the master is sending data, and in that case, the slave is going to give us the ACK or a NAC if it's the last thing, or if the master is reading data, it's going to give the ACK or the NAC. And we always have a NAC on the end of a read. So you'll see that here on the on this block read. So here's that restart, and here you see we're sending the read code. The only difference between this and this is bit 1 is set. Now, I did it this way with constants because there is only one device ID. you'll see in other programs, I may have a variable called device ID because it's got the device type plus the address built in. So I will do this for the new address because I want the device ID, but I want the write bit set to the read write set to read. So if you see that in my programs, that's what's going on. We don't have to here because there's no addresses. It's always 0. Now you'll notice for the read block, we're subtracting 1 from n. So we're doing this, and when we do a read, we have to set the ACK level. So in this case, it's ACK, which is pulled to 0. It's telling the slave, hey, we got it. The very last byte of a read transaction will be NAC from the master. So you'll see this throughout. And then finally, a stop. So this routine, generically, you'll have in almost any I2C part that you do. And you can use it then to do 1, 2, or 4 bytes as I'm doing here. So it's the same kind of thing. I'm using that generic read routine. This is saying get 1 byte, put it here, and this is the register that I want to read. Now, this works as well in the propeller because you remember this is a return value and it's always pre-initialized to 0. So we don't have to worry about any extraneous noise in our return value. So this always works. So we can do multiple bytes here. In this case, I want to be able to read the time. That's what I was doing in the demo. I was saying, hey, just give me the time and put it wherever I tell you to. So if we look over here, I have these 3 bytes set up, seconds, minutes, and hours. And read time is grabbing those registers out of the RTC and putting them into those variables. Now what I'm doing, and you can see I'm boringly consistent with the way I write code. If my new seconds value is different from my last seconds, I know I need to refresh the display. And so that's what this does. And since we have a new second, I'm grabbing the temperature out of the clock and then updating the display. And I have a thing, because occasionally terminals will get screwed up. So that's what this does. I do this all the time. If I mess up the terminal because I make it too small and it screws up, I press the escape key and it does a clear screen. And oh, you know what I didn't do is I didn't adjust that for the ANSI terminal, so that'll have to be fixed. But here's the challenge now. Again, this stuff's pretty easy. Is take the last program with the encoder and the LCD, put the RTC in it, and set the clock using the encoder. Make a clock on a timer. That'd be a good challenge. That'd actually be very useful. There's a gajillion things that we need timers for. Make a kitchen timer. The first time that I did a rotary encoder, a guy called me and he was doing, you know, he made a timer for growing plants in the nursery. And he had an LCD and the encoder, and he was doing things like that.
I was thinking of an easier version, John. Just set the time and display it on the LCD.
Oh, that'd be fine. Yeah, start simple. Always start simple, but then build up. You know, or yeah. Or even since, you know, you have the ability to set individual things, technically you could do this without an RTC as well. Since the Propeller has internal timing, you could make a countdown timer, you know, where you're setting it. And if you want to hook up the real-time clock, then you have time of day plus countdown. There's all kinds of things you can do. It's just, again, these little building blocks, taking them, putting them together, and doing fun stuff with them. Okay, final demo, and we can wrap up. This went longer than I thought, is EEProm, which is also on your RTC module. So you got the clock and you get a free EEProm along the way. EEProm storage is how the P1 works. So that's where I started dealing with I2C, you know, a lot, because on most of my my Propeller designs, then, you know, I have an I2C connection that goes off the board. So this is a controller that EFX Tech makes. And in fact, this little 4-pin header I used all the time for hooking up these LCDs. Yeah, I've a gajillion times, I have connected an LCD and an encoder to this thing and made escape room puzzles and stuff like that. It's a very useful thing. And in the Propeller 1, we have an I2C bus already defined because the Propeller 1 uses EEProm for its program storage, where the P2 uses flash. So the EEProm demo is really very simple. In fact, it's the most boring of them all, I think. And what it does is it will erase the EEProm and then just show you that you can read and write. Oh, see, this is why I do those clear screens. So let me do this again. I have a wide screen for this. So in the demo, if you look through it, it erases the EEProm. Now, here's an interesting thing. You'll find this with EEProm and with Flash. When you erase it, well, I'm erasing it deliberately to FF because that's what the manufacturers do. When you get an EEProm, if you look at it, it will have all ones in every cell. And then here, so this is erasing everything. And this dump is what this little routine is what creates this display. So here's an address, and then there's 16 bytes, and it's like an old style DOS debug display. If there's ASCII characters mixed in there, it'll show them to you there. And then we're using the features in the EEProm object where we can write a byte, a word or a long or a string. Now remember, in the Propeller and most other languages, a string is an array of characters terminated with a 0. And that's a 00 or a null, in many languages call that. It's not ASCII 0, which is technically 48 is the ASCII code, but a 0. And so in fact, if you look at this, if you look at the dump here, so this is Propeller 2, and you see that 0 is the terminator for the string. And so you can see it's really quite simple to add non-volatile storage. And the upshot of this is that when I turn off my kit, those strings will have stayed in there if I need them. So we can use that for backing up data. In many cases, like the board I just showed you, all of my P1 designs, I use a 64K EEProm versus a 32 that the P1 needs. The reason for that is a lower 32 is used for the Propeller program. The upper 32 I can use for anything I want. I've talked many times about the laser tag project that I've done and I'm working with again. It uses the upper 32 as all of the configuration storage for the, the tagger, and so that as we swap out applications, which we have to do in that case, those things are protected. Even though we changed the lower 32, the upper 32K is protected. Now, what what we need to have is something similarly easy for the P2 flash, and I think he has mentioned in the forum, so I hope I don't get in trouble for saying this, but Mike Green is working on a flash driver where we can treat the flash on the P2 as file storage. So that will be very, very helpful. Okay, it would get, well, it's been redundant for a little while. I'll just wrap up by saying this. I2C is very, very easy. Hopefully you've seen that and thought, oh, hey, that's not so bad. And it's just those 4 transaction elements. And then, we added in like the block read and the block write to save some time in certain things. But you really should be able to go grab any kind of I2C widget. And there are, go to Amazon, you'll see gajillions of them. Get the widget and write the code for it. You won't have any trouble.
John, I think you put us like years down the road this evening between the I2C sniffer, address, education, and now the real-time clock object. And
Well,
the
yeah, hopefully
LCD
everybody
has that.
sees that, you know, the elements are all the same in there. The
Yeah.
I2C is really the fundamental core. And you can see, look, we have three discrete things. We have this display, we have a clock, and we have a memory that are all using that same bus and the same transaction rules. And there are hundreds of I2C devices out there that are useful and that you can put to work. So there, for example, there's, you know, now the nice thing with the P2 is that we have analog capability, but in many cases with P1 projects, I used I2C ADCs so that I could read potentiometers through into the P1 by using an external I2C ADC. But there's lots of fun things out there. And now hopefully you've seen that they're really simple to program. It just takes a little bit of work going through. Again, if you follow the transaction diagrams and you look at the, you know, these examples, you'll see, you know, how, where is it? These steps are, that's all there is to it for any I2C device. It's really, really simple. And you can take that, if you look at that code, if you, in fact, I would suggest get the DS3231 data sheet and look, and you'll see this in their rules, and it will link that code to what's happening. That'll make moving to another I2C device very, very simple. So again, the, where was it? The little encoder from SparkFun. You know, they had, this is not a traditional I2C device because they're using a microprocessor on there, but they set it up as register based, and they said, here's where you get this value, here's where you put that value, because you can change this, you can write to the RGB colors. So there's writing to it, and there's obviously reading back for you know, what its position is or what its limits are. There's lots of things. So have fun. I like I2C. I use it all the time.
John, at this point, have we used all the parts in our kit?
The temperature sensor is the only thing we haven't used.
Oh, okay. Yeah, I was confused because suddenly we had it on the clock. So we'll be using that next week then.
Yes, and I
what's
should
the
probably put up or shut up and make a little temperature alarm based thing, since we have an encoder and we have a temperature sensor and we have a display.
The temperature is also I2C?
No, the temperature is one wire. That's a new
One wire.
topology.
It has 3 pins, power, ground, and then
Yeah,
a signal on
it's
it.
one wire. It's power, ground, and signal. So it's remember I2C we called synchronous serial because it has a clock. One wire is a form of asynchronous serial because there's just a data pin and everything is timing related. So that's where, you know, as I said earlier, you can write I2C code, grunt code in any language, high or low level, doesn't matter. I choose to use embedded assembly so I can very precisely control the timing, because you will see that. So I'll give you a real world example. This little I2C display, that it's got a little 7-segment display. There was a guy who was helping with, again, another escape room prop, and he wanted this on the propeller on this board that has an external I2C port on it. We put it on, and everything was fine when I was just downloading to RAM. But as soon as we tried to boot, there was a problem. And the reason was that the boot sequence for the P1 ran much faster than this guy could tolerate. And so this interfered with booting up. And what I ended up having to do is moving this to a new set of pins so that the P1 wouldn't outrun this and have this create garbage. So that's why, you know, I do like with the P2, I have absolute control over what its speed is. And I'm able to deal with contingencies. In fact, when I had that encoder, it kind of worked. And so I thought, well, maybe they're being a little bit overconfident on their clock speed. So I brought the clock speed down, since I can control that in my object. and it started working. And so I thought, okay, they're liar, pants on fire. They can't do 100 kilohertz. I have to take it down to 50. And then I tried to do that transaction where it reads back 2 bytes, and it failed again. So that's when I dragged out the logic analyzer and found that it was clock stretching. And so I put that into the driver, and now it works really nicely. So, you know, my I2C driver is still fairly fresh. So if you find a part that gives you troubles, please let me know and I'll look into it. But, you know, I2C is so useful. I do want to make sure that it's covering all the kind of corner cases.
And John, I have a question too for everybody who's participating. I don't want to hurry along the content and how fast you're feeding us, but thinking ahead and looking down the road, I'm curious about the types of things people would like to learn about with the P2.
Well, may I make a suggestion?
Please.
Because I was thinking about, we haven't really talked about serial, although we've been using it, but now we've done I2C. Next week we're going to do is one wire. But I mentioned it in my presentation today, but what we haven't talked about, and there are smart pin modes that can support it, is SPI, which is a very common bus. And I thought I had a part out that I was going to suggest that we could use because it's a common Amazon part, but it's a little 7-segment display that's got 8 digits that you can get for $3 or $4 from Amazon. It's got a 7219, whatever that chip is, and it uses SPI because that's another common bus topology.
And how about some of the smart pin modes for driving servos for PWM?
Well, I mean, the nice thing is that, you know, in fact, one of the things that we could probably do is, because the smart pin driver that I wrote works, you know, we've seen Kevin put it to use, so that's kind of neat. But the smart pin mode on the P2 is kind of a dumb servo driver in that it will just hold position. The smart pin doesn't have the ability to do ramping or any of that kind of stuff like we have had in advanced servo drivers. So what we can do is show how we can take 2 approaches. We can either use that timing kind of thing like I was doing with the button deal to see, hey, is it time to update my servos? Or we could actually have a servo manager in its own spin cog that is just constantly doing that. So we can ramp servos and, you know, create animation cycles, like if you were doing a walking gait for a robot or things like that. And that's where the multi-core aspect comes into play really nicely, because you can have a whole independent cog running on its own doing that thing while the smart pins are creating the pulses. It becomes a really nice kind of set of opportunities.
Yeah, so the programming challenge becomes the pulses and the sequence more than the signals, the generation is handled for us.
No, the pulses are no challenge at all with the servo object because the smart pin generates those automatically. Now, what we may want to do is start them with an offset so we're not pulsing all the servos simultaneously, but that's very easily done. And after we've done that, once you've set up the servo smart pin, it's running until you stop it. All you have to do is give it new values. Yeah, it works really nicely. One of the, excuse me, one of the things that I'm working on for Rick is the ability to read the RC pulse that normally goes to a servo from a receiver so that he can take that and he can do something with it, you know, on set, controlling a puppet or something. Excuse me 1 second.
So while John takes a drink there, anybody want to shout out other things they're interested in?
Yeah, I've got some. Any of the new click modules that Parallux is selling, it would be kind of fun to be able to program some of these. This is the OLED. I've also got the LSM6DSL. Kind of fun to walk through setting because I think one of these is I2C and the other one might be SPI.
Yeah, great idea.
I was gonna say with the I2C, you already know how to program like half the clickboards.
Yeah.
Yes.
Yeah.
Well, and that's Roy. Thank you for saying it, because that's the other reason for talking about SPI somewhere in this mix, because the microbus is a conglomeration of standard serial, I2C, SPI, and a couple of extra signals you might use here and there. So by having, you know, seen everything kind of at the root level, then you know, as you just say, now you can program, you know, or at least you have a fighting shot at programming any of the click modules. I've written 7 or 8 click module objects. I've got more. You know, I've got a pile of clicks here that I'm working with, and so we will go through that. But again, reiterating what Roy just said, it's 3 basic protocols that are being used on the clicks, or one of the 3, if not a mix.
Yeah, I would be especially interested in, you mentioned serial, John, you know, interfacing to some serial type devices and reading and processing data streams.
Yeah, John, there's a question from the chat about the formatting string used with the %.2x and %.4x and %.8x. I tried to explain it, but I think you would do a better job.
Okay. Yeah, and this is one of the things I should probably, you know, maybe we should pop down to San Diego. So we, I guess you and I are locked down in California. We couldn't meet in public if we wanted to. Because, you know, what I try to do is mimic what printf is doing in C and Python and those kind of languages. But the % lets you do a formatter. Now I have a cheat in there. If you look in full duplex serial, there is a private method called get, I think it's called get nargs or something. Yeah, get nargs. This is short for get numeric arguments. And when after the %, you can have numbers in there. And so it will look for 2. When it sees the decimal point, it knows we're on the second number. Now, because these values are pre-initialized to 0, if we don't put the first number there, then it just assigns it to 0. So that's a little cheat on my part. So the idea is that if I do %. You know, 2, for example, with the hex, it's going to be a 2-character wide hex in a field width of 2. Does that make sense? It helps to understand the printf, you know, kind of stuff.
Yeah.
Where was I? Let me find one of the programs where I was.
That was the one where you're reading the EEProm back.
Oh, okay.
Reading and writing the EEProm.
Yeah, okay. Yeah, so this is just string stuff. My screen is showing, right? I'm still showing?
Yep.
Okay, so this is the control character telling the F string, okay, I have formatting stuff coming along. And now normally I would say you would do this. You would say 0.2 because you were saying make the field as wide as it needs to be. That first digit is how wide you want the field to be. And then this is how many digits to actually print. So for example, if my value was 0 and I didn't have that in there, I would just have 0. But by doing this, it forces it to print with 2 digits, so it'd be 0, 0. So again, it's just being, you know, maniacal with what the output looks like. That's why we always consistently, we get 2 digits here. And here's that case where there's 0 and it prints as always as 2 digits because I've told it to do that there. The same thing with the word, I'm using 4 digits and 8 digits. And in this case, I don't have any extra space. So for example, well, let me just do this. I'm going to put a 6 here. So that's going to make the field 6 characters wide, but I only have to print 2 digits. If I run this again, you'll see what happened is that there's the 6 characters of the field. By either having that 0 or not putting anything there, then it will print the field as wide as it needs to be. And in this case, I have this adornment in front of it because I want to show, hey, this is a parallax hex value. So that's why I'm doing that, so that I just get the value out and I don't have any padding in there.
So does it support the full printf
I
coding or most of it?
I think most of it, I have sitting very close to my desk. I have the, version 1 K&R, which has a description in the back, and I was going to go through and test everything. So it's likely some changes are coming. I want it to match what full printf is doing to the degree I can. I don't treat octal the same way, and because we don't really use it. I mean, I have octal as an output format. You can see, it's there. But for example, when I do control characters, if you do a control character in a normal printf, it's assumed to be octal. In my case, it's assumed to be decimal. So if you do a backslash and numbers, it's going to take it as a decimal. It's not going to treat it as an octal. So there is that difference.
Okay,
But
yeah.
by and large, it's pretty close. I know that Ray Roddick has found it very, very useful. He sent me notes a couple of times that he's found it useful. So I have found it useful. But this is also fairly new code to me. So I'm open to suggestions and improvements, because that is one of the nice things about, in older languages like C that have these really nice libraries that do this stuff. And the ability to do nicely formatted output is a good thing. And so one of the things, though, that I'm also considering on this topic is, all of this stuff is the formatting stuff and all these other things is actually putting it into a separate file and then so it just converts whatever you want into a string pointer that you can print with anything. So for example, today when I was doing doing the LCD program, I tried to do, an F string, with a number on the LCD, and I didn't have it built in. So, I had to use one of the other things. So we want to make it a little more global once we figure out what the rules should be. So this is, as ever, George Lucas said, movies are never finished. They're just abandoned. That's the same thing with code, I think. It always will go back and try to make improvements to it. So, if you find anything, well, you're not doing a lot of spin programming though, are you, right? As you do more, if you find something, please let me know.
Yeah, I do mostly the C or pasm.
Yeah.
But I've been using your drivers because Eric's C allows you to include them and call them directly, just like from spin. It's very nice.
Yeah, that's useful. I actually did, when he first said that, I thought, come on. And I tried it and I thought, oh, heck, it works.
Roy,
yeah,
I
so
would
you
love for you
can
to
use
share
the
that
drivers with,
someday.
and then write your main application in C. And then, I was looking at your code today.
So Ken, I did share it already on the forums on the P2 Christmas light thread. I shared a video of the Christmas tree, and then a little while later, because I was up pretty late last night, I shared the code for an enhanced version of what was in the video.
Okay, that's an example we'll bring into the Quickbytes to give it the right visibility in the future.
Just a short C program, and it includes JonnyMac's Spin 2 code, so you need to get his library files and put them into your samples folder along with that on FlexProp, and then you can run them all.
But then the nice thing is, most people are going to treat libraries as black boxes anyway. Once they have them, then, and I didn't look at the interface, and I don't remember what it was when I did that demo. Is it a lot of effort to connect a spin object into C as a library?
No, it's literally one line to specify it, where you tell it the name of the spin2 source file and a name to use it in your code, just like in spin2, and then you literally use that name dot whatever and call all the functions, and it just handles it for you.
Well, that's really good for
code.
Yeah, people that are doing C, but need a driver that's already available.
Is this it, Roy?
Yeah. See the two struct using JM lines there, right near the bottom of what you have?
Yep.
That's how you include the object to use it. And then if you scroll down, you'll see where I use LEDs and encoder, and I call it just like JonnyMac does. And I
Wow.
used his same definitions that he had in his con. I made defines in C for the same names. Like you can
Nice.
see BTN, debounce, and all
Yeah.
those defines.
That's a heck of a leverage of code in a direction that a lot of people really want.
Yeah, and this code, like all the rainbow and theater chase and color sweep functions, were originally written in Blackly prop and exported to C, and then I cleaned them up and changed them around because in Blackly prop you can't pass parameters.
Yeah.
So I changed it from global variables to passing parameters, and that's the only difference.
Neat. That's really cool.
And you know, we have the simple tools header in FlexC, which gives you some of the niceties of simple tools, like you can just do pin high and pin low and stuff like that, and other simple things.
Excellent.
Fantastic. Yeah. I wonder what the
since
C
it's-
programmers think of this.
Roy, have you done any evaluation? I guess we should probably ask Eric, but you know, I think there's the guy Ray who was in the forums, and he was a little worried about using spin objects because he wants to program in Flex Basic, but it's the same compiler. So is it reasonable to think that the output is going to be the same regardless of the language that is used?
It's very close. Like some of the different languages sort of have different constructs for how they work with data or how they call functions and stuff like that. So there's occasionally very minor differences, but at the end result, the PASM2 that it's running in hub exec mode with FlexProp results, they're pretty close to the same. Sometimes the instructions might be in a slightly different order.
Yeah, but
or might use some slightly different things, but they ultimately compile down to the same thing.
right. Yeah, here we go.
So the video doesn't, it's the first version where it just plays everything one after another. The code, I added reading the Quadrature encoder, and so you can change the mode between the different sequences that it's playing with the encoder, and then if you push the button, you can change the brightness. So you push the button and then it changes the brightness, and then you push the button again, it goes back to changing the mode.
Nice.
I love that, Roy. It's so Metropolis looking.
Yeah, I quickly laser cut that wood form that the rings are on last night at like 1 a.m. and then made that video.
Nice.
You should put Mariah, a statue of Mariah, right in the middle of it and have the ascending rings around her.
Yeah, I could do a version of that. I just need to find the art because I'm not an artist.
I'll send you a Mariah. I've got several sizes of them 3D printed.
Okay, no problem.
Oh, before I forget, and I see Dennis on the screen. Dennis, did you happen to try that processing demo that was in the files last week on your Mac?
Yes, I did, and it worked.
Cool. Would you try, if you would, go to the file menu and see if it'll export to create a Mac application?
Oh, okay.
Because I noticed this on the Windows side, at least in the Windows version, you can export to a Windows executable or to a Linux executable. And I tried it work. So the goofy little robot thing, it created an exe file and it ran fine. This is good because I was with my friend John yesterday, and you know we're doing this project that we finally got wrapped up that is a target controller for a shooting range. And we had all kinds of craziness going on with what ultimately now is a simple project once we understand everything. In fact, I was telling Ken this story earlier. The output, remember when in the beginning when I was showing all those crazy I2C transactions and it had the clock stretch and all of that thing? That was from a $12 logic analyzer that I got from Amazon. And it saved my backside on this project with John because I was struggling with, we had, you know, it's not terribly short, but what happened is the master controller, it's two P1s that are talking over RS-45, and you can imagine the master controls a frame time, and it's going to send a command message. The slave device, which is controlling the actual motor and the target stuff, it has to do some processing and deal with its own state machine, and then it has to send a response packet. And since we don't know, you know, if things are going to, you know, what their wires are going to be, I always just run the packets through a CRC algorithm just to make sure that we're okay on either end. And I've been using the same CRC code forever. It's not even code I wrote. It came from Micah Dowdy. She wrote it a long time ago for, it's the CRC8 out of the one wire. So we'll see it next week, actually. Anyway, to shorten this long story, what I found out is that my spin code on the P1 that was doing the CRC for those long packets was taking so long, I was violating my frame time. But I found that using that logic analyzer, because what I did, it's RS-45, so I got one of these cheap RS-45 boards, you know, from Amazon that, you know, just have the RS-45 components on it. And I stuck it into the system, and I took the digital side and ran it into the logic analyzer. And I was able to, we have some extra pins on both sides that I was able to bring into the logic analyzer and say, hey, this event is now happening. So at the start of the frame, I could take a pin high and I could see that on the logic analyzer. And that let me see all of the timing. So two words. Now, professionals, we also have, I mean, there's, you know, like a company called, I think it's pronounced Soleil or Soleil. They make really nice logic analyzers. They're a little on the expensive side for hobbyists. Yes. I
have a Saley, and
yeah,
it's really
Saley.
nice. It also does scope as well as logic analyzer.
Yeah, they're super nice devices. For casual hobbyists, a little on the pricey side. So there is, if you want to experiment with that, and I encourage it again, you know, if you just look up logic analyzer on Amazon, you'll find this $12 device. And it's interesting because when you look in Pulse View, it mimics the data packet kind of of the expensive device. And you know, it's not going to be useful for super high bandwidth stuff, but I used it on this. I found that clock stretch problem on that encoder, and I think Bob Sweeney was trying to use some older style smart pixels over the Thanksgiving period, and I didn't have any, but I wanted to help him, and I like writing code, so I just hooked that up to the P2, looked at the signals. Oh, there he is. He's on my screen now. And I said, here, Bob, try this. And he said, hey, that works. There it is. Yeah.
There.
So it's
got one right after you told me about it.
That's $12 I spent in the last couple of months.
Yeah, the only real difference between the $12 one and the expensive one is the ability to go at much higher clock rates.
Data rates, yeah.
And then obviously the higher end Saleys have analog as well, so they act like a scope on every pin as well.
But you know, I would encourage people, you know, and in fact, I've told all of my friends. I don't know if he's still online. I was speaking with my friend Rocco yesterday, who's getting into this. I said he was on Amazon buying some stuff, and I said, here, let me spend another $12 for you. Get one of these, so that you can see signals and learn things. And again, as Roy just pointed out, it's not going to be for really high bandwidth stuff, and you can't do analog with it. But for the kind of signaling that we're doing here, the I2C, even the one wire, I used it when I was rewriting my one wire code for the P2, because that's all in assembly. And I wanted to make sure everything was doing what it was supposed to do. So I hooked it up, and it did. And the nice thing is, even Pulse View, again, it's a really nice piece of cross-platform freeware. It would show me, it has an I2C, a one-wire decoder in there, so it would show me. And so there are inexpensive tools for hobbyists that can help the hobbyist, and you know, and those of us that are pros and do this kind of casually too, can really help you get the most out of what you're doing. Because it can be frustrating if you don't know what's happening. You know, my friend John, he'll tell you, you know, I live down here, you know, get a little frosty with my language at times. Yeah, I was a little potty mouth on that project until I finally understood what was going on. I was like, okay, that visibility into it. So, you know, that might be a topic too of things. Hey, let's look at this. And remember too, the Propeller also has scope modes, and with the new debug output stuff, there are some opportunities to be looking at signals right inside the Propeller too.
Hey, John, is that the HiLetGo that you're talking about?
I think that's the name of it. Yeah.
It's like $12 or something on
Yes.
Amazon? Okay.
Yeah.
Thank you.
Yeah, and then if you just do a Google search on Pulse View, and get, you know, whatever, you know, for whatever operating system you have. One of the things that I was looking into, but time was not on my side during that, is because you can write your own, protocol analysis tools for Pulse View in Python. And I thought, well, that'd be useful for some, you know, some things that I was doing. I haven't figured out how to do that yet. I'm reasonable with Python, but not great at it.
Yeah, there's a whole bunch of different of those devices on Amazon, ranging from like $12 to $20.
Yeah.
Coming with various different wires. Basically, is the main difference on them. They're all the same thing inside.
Yeah. Yes, they are. Yeah. You know, most of them are shipping just, you know, the thing, I think it's just the high speed USB is what is really the critical element. So you can get the samples into the computer. I'm sorry, Dennis, were you going to ask me something?
Yeah, on that asking about processing. Yes.
Yeah.
From a Mac, you can export Mac OS, Linux, or Win executables.
So that's really neat, because now this is you know, going to, you know, the question Carol had in another session, you know, can we use processing? But now we could actually create standalone tools. And as I was saying, I was showing John this yesterday when I was, you know, visiting with him, and we thought, because we have these kind of complex debug screens, we thought, let's just blast a big block of data into processing and do it visually. Because the packet coming back from the target controller tells us where the hard limits are set, where the soft limits are set, and where the device is and how fast it's traveling. We could put that on the screen visually and have it, you know, see what's happening, you know, quickly. I mean, we see, most of us anyway, it's easier to analyze a graphic than numbers. And that would be, you know, I think from a thing, you know, thinking about the kind of stuff that Ken teaches often, that would be great for building little robot controllers and that kind of stuff. Because the next step for me is trying to, you know, figure out or implement it nicely, how to get data from processing back to the Propeller through the serial. And it's just a serial connection, because you think about it, you know, if there are kind of UI elements built in there, then you could do a whole kind of control board thing for lights or anything else for that matter. And I think that would be kind of a fun community project, since processing is cross-platform and available to everybody. Doing interesting things with the Propeller with it, I think would be a good way to get more people from outside our community into the community.
John,
Maybe. Yes, ma'am.
I'm already working on that. I will have it done in a couple of days. I'm using the evaluation board right now, since I haven't got my edge board up and working yet.
Okay. Yeah, it doesn't matter. It's just serial, but put it in the forums or it doesn't exist.
Yeah, it'll be something new, different.
Okay.
What we
Yeah,
did
and
before.
you know, I mean, I did that silly little program, but it was just an idea to see, you know, if we could do that. I know we can, and in fact, I just got, when I got home last night, I had an Amazon package waiting, so I got the Python processing book, because I like Python. I'm trying to get better at it, so I'm going to try it with that as well. The trick is, what I really wish about processing is it had kind of the VB ability to make nice, you know, standardized looking user interfaces. I don't know if that's the case, but
Oh
I
yeah,
can probably.
yes, it is. literally nothing graphically that you really can't do with processing. And
Okay.
you can make some very structured looking outputs if you want to. In fact, when I did my thing with an Arduino and processing, the grid that I made it to fit the resolution of my screen on my computer. And it turned out that the feedback I was getting, I was reading centimeters of distance. This was with pings. And my grid exactly matched what my pings were reading.
Nice.
Yeah, so there's a lot you can do with processing, but I will have one ready before the next thing using P2 and
Excellent.
yeah.
Hey, you know, again, you know, the P2 is new, and those of us, and most of us in this call, we've been around the parallax world for a while, and I find that when I'm speaking with new people, even my friend John, I just spent 2 days with my friend John, and he's been using the P1 in his products for ages, but he just really didn't, I don't think he quite grabbed onto the P2. And after yesterday, okay, you know, and now he started seeing things that I was kind of throwing out a few months ago saying, well, what about this? What about this? And he actually, it was funny, I didn't say it to him, but he presented an idea to me that I had talked to him about, you know, I think 4 or 5 months ago, which is good because, you know, he's now seeing the value of the P2. And I know because you look out in the world and you see people, you know, that are using other products that are doing really neat things, but then in other cases having a lot of frustration. And the P2, well, the Propeller family in general, but I think the P2 specifically brings a unique set of tools that allow people to tackle problems and not tackle the process of solving the problem. I hope that makes sense. Well, you know, in every processing literature that I've read so far, it's all about being productive very easily. To me, that's what the Propeller is. It's not traditional, for sure, but I don't care. What it does is allows me to solve problems very quickly and very easily. And, you know, I would arrogantly put up the proof as here, Kevin, within an hour of having the board in his hand, was writing custom code. And I think that just is, you know, it's obviously a tribute to his intellect and his wherewithal, but also the ease of use that we have with the Propeller. And I just, you know, I want to shout from the rooftops at times to people that aren't using the Propeller, why not?
Well, if Ken can post it, because I'm in my bedroom actually. I'm not with all my computers. I posted a link to something I did for the ballet. I was involved in a ballet performance in that I had robots in the ballet that I controlled, and some of them were parallax robots too. But in keeping with your LED projects, if you look on the girl, you will see she has a heart that was sewed into her dress. And I'm off stage controlling the beat with a remote control. I like to simulate that using the Propeller, that same heart we did.
Well, what do you mean simulate that, Carol? Do you want to control those LEDs? Ken's got the, well, I guess you're saying Ken put the video up.
Oh yeah, they're just, in that they're controlled by a remote controller. I'm off stage doing that. I'm also running the red dancing robot, and Bill is running the following robot. That's a lead. Yeah. We had a whole string of those.
Yeah, I can see the targets on them.
Yeah, and by simulating it with the P2 is I'd have to use like the Mini because it goes into a costume.
Yeah.
Because these guys want this again in another ballet.
So you just need to do the heart beating, but you don't want to have to control it off stage.
No, I don't mind controlling it off stage.
But if the beating doesn't necessarily have to be synchronized to anything, or you can just get
yes, it does. In the story that goes with this, she starts off as she's a robot too.
Yeah.
and her heart doesn't beat. And then as she gets more and more human, her heart beats faster and faster and faster till it gets to a normal heartbeat.
So
And we
is
didn't have
there
any-
a microcontroller in the costume now that is doing something?
There's a lily pad.
Oh, okay. So there is some
I
code in
used the
there.
lily pad for that.
Yeah.
Yeah.
Okay. Yeah.
Yeah.
All right. Well, if it can be done on that, it can be done on a propeller.
Yeah, it's just a matter of getting one small enough to put inside the costume
Right.
because you can't restrict her. In this particular scene, this was just me and her and Bill practicing movements between the robot and her to try and get things where her and the robot look like they might be doing sort of the same things.
Sure.
And actually in the ballet, it just turned out stunning. And the whole thing was just fantastic.
I did a
That's another
heartbeat.
character in there, that little yellow guy coming in.
I did a heartbeat thing for you know the Disney in Haunted Mansion, the bride that has the heart in her chest. You know, that's kind of a gauzy looking thing.
Yeah.
And I used you have a really nice shape there. This was a very quick project. It was a Halloween thing for a local makeup artist that I am friends with. And what I ended up doing was creating, because I used a WS2812 panel and then created the heart shape on there and then animated the brightness too. And it worked out really nicely.
Yeah, they wanted the costume designer to do this and she had no clue what to do. And then I said, well, I know how to sew. So between me and her, we've managed to get it into her costume with battery and everything.
Yeah. Neat.
Yeah, super application.
Yeah.
Yeah.
I had a question
Yes, sir.
for John. I'm a beginner and I appreciate your presentation. Very interesting, very a lot of good information. What's your recommendation for beginners for starting drivers? I guess, can you point to in your code, it looks like a driver to me is just another object that you call throughout your programs.
Yes.
Obviously, I'm going to look at your drivers because that's what part of this demo is about, and I appreciate it. But what do you recommend for a beginner to obtaining drivers and then how to use them or implement them?
Well, most of us, and I appreciate your kind words, most of us that are writing objects, and you'll hear me call object driver, it's the same. You know, typically, well, we might consider a driver as an object that is going to be dealing with a piece of hardware. But what we like to do, and I try to do whenever I write a new object, is create a little demo for it so that, you know, you put it to work. And, you know, so that's, hopefully you'll find that if somebody writes an object for a widget or a device you need, hopefully there's a little bit of demonstration code. It's I think, you know, probably 90% of the time that happens. I don't remember very often seeing somebody write an object and just say, oh, here's my object, do what you want with it. You know, it's nice to have a little demo to show it off. And so the key, though, as I said earlier, so if you're looking for a driver, so now you have some exposure to I2C. I don't know if you ever had before, but now, you know, you've heard a lot. Remember, too, I think I said this last week, but if I didn't, I'll say it now. I worked for a guy named Bob, who was a nice guy, and his favorite thing to say was, a human being has to hear something 5 to 7 times before it sinks in. So if you're feeling a little bit like, holy cow, this is a lot of stuff, it is. And the idea is now, you know, hopefully you'll go back and, you know, of any of these devices that we use, maybe one appeals to you more than the others. Get the data sheet, always get the data sheet, read through it. Some of that's going to be thick too. But you'll notice, especially now that you have references, and I would suggest if you're interested in I2C, which is I keep banging on about, is a very, very useful bit of knowledge to have because it's such a well-used protocol. It's been around 40 years, and there's so many devices that use it. You know, there's lots of generic internet information on the internet. that will match up with what I was telling you today. And I would suggest start with EEProms because they're very easy and they're useful too. You can store data in them and learn how those things work. But whether it's I2C or if we do SPI later or one wire, pick a topic and work through something and make something. Because, you know, you can't learn to ride a bike by reading about it. You have to get on the bike, and there's just no two ways. And it applies to coding too. You can read about coding, but you got to write some code. Be careful if do you go by Nicholas or Nick?
Nick's fine. Thanks.
Nick, are you an electronics person?
No, I'm not. I'm a mechanical and nuclear engineer, but I do work in I&C world. But I'm trying to learn more about it by getting exposed to this propeller chip.
Nice. Well, you know, so here's the thing. You know, in my very first presentation, I said, you know, as programmers, we're doing something a little unique because we're dealing with hardware. You know, if we're programming our PCs, that hardware is all connected and you really can't go wrong. You can't break a circuit writing a bad piece of code. Since we're connecting things, you can break things. I mean, Ken talked about it, Carol talked about it. I mean, so you do want to learn some of the basics of electricity and the electronics, because my cheeky phrase is, it's Ohm's law, not Ohm's suggestion. You have to follow those rules. Now, they're very simple, and certainly a mechanical engineer that works in the nuclear world, this is not going to be difficult stuff for you. But don't take it for granted. Learn the rules, learn Ohm's law, learn series and parallel circuits, learn the interactions. And most of the time with microcontrollers, we're doing very simple circuit things. But you still need to understand those rules so that you don't go wrong. And if you have no exposure to electronics, it's a book that's as old as me nearly, but it's so worth having. It's called Getting Started in Electronics by Forrest Mims.
Yes, definitely.
I'll bet half of the old timers on this or more have that, you know, on their bookshelf as I do. And it is a great place to start. It's the most non-threatening start in electronics that you're ever going to find. And
I have all his books.
Yeah, exactly. He's a gem, you know, and you go all the way down to, you know, that's on one end, and then you have, you know, this giant thing, The Art of Electronics on the other.
There's a workbook goes with it too.
Yeah. So again, you know, the understanding those things, and then I think, again, I said this in the first presentation, it's easier to learn something if you have a goal. Just generically learning. That's why I'm trying to create something fun to do with processing, because it'll force me to learn it. Just going through and reading the examples of the book, I get bored really easily. So I'm trying to create a specific task for myself that will be useful for me and the community that I can develop, because it'll force me to learn processing. So do that with a propeller. I mean, do you have an idea now? Like if you knew what you know, I or some of the others know, what would you do with the propeller? Do you have something in mind right now, or is you're just at the start of learning?
No, I do have an idea. So for the company I work for, we send out equipment into the field and we actually plug it in and measure signals from the nuclear plant, and we basically measure the core. And I'd like to we have something, it was called the Rocket, and it was like an old analog box that we plugged in, and we simulated signals like we were in the field, but we weren't, and we just calibrated or checked out that our hardware is working correctly. So I'd like to make a box, or use the propeller chip and send out basically analog outputs that will go into the system, and it will, but I have my backgrounds in like dynamic equations and doing simulations of what the plant's doing. And I'd like to use my, you know, discrete equations and then to do the calculations in the propeller chip, but yeah, send an outputs that represent like what we're measuring, so that we can test or train other people. And it would end up outputting some voltages, and then some, we actually have to measure like micro or pico amps, so current too.
Wow. Yeah.
And yeah, and I'd like to use this chip to drive that and set up different scenarios that we can train people. So basically a simulator that actually plugs into the hardware.
Well, Nick,
Yes.
one little piece of advice from me on that is there's not a single project I have ever attempted that I have any clue of how to do it before I start. Everything I've ever done, I jumped into, and I goof, I fix it, I goof, I fix it until I get it done and I can do it. So don't be intimidated by not knowing what you're doing before you start, because I've never started anything that I had a clue of what I was doing, really. That's just sort of my advice on it. Do it anyway, whether you think you can or you can't.
And I mean, that's a really interesting idea that you have, Nick, and it's a fairly complex one, which is cool. So break it down into simpler parts. The P2 can do analog, so learn how to do that. You learn how to configure the smart pin. You probably will have to, depending on what you need. Now, unless you need 0 to 3.3 volts, or even if you do, it'd be better to buffer it. For example, the project that I talked about earlier with my friend John, we're sending a 0 to 10 volt signal to a motor controller. And so we have, now that's a P1, so we have another little bit to create the analog for us. And then we're going through a simple op amp to, take the voltage from 0 to 3.3 to 0 to 10. And, just like my little code segments, you might have seen, I'm doing little chunks of things that I reuse quite a bit. We all do. It's human nature. And you can do the same thing with your electrical circuits. When I was speaking with my friend John, he's built a wide variety of projects, mostly camera. His industry is camera controls and platforms. And we have various circuits for driving motors, driving, lenses on professional cameras and the works. And what I suggested to him yesterday before I left is, let's go through all these circuits we've designed and modularize them and say, okay, when we need a lens controller, here's our little module. In fact, the clicks came up a minute ago. A lot of the circuits are fairly small, and I even suggested we use the microbus format for his modules, so that he could put clicks in there if there was the appropriate one available, or other people could use them too. But
comment, Sean. I have a comment when you're done too.
Oh yeah.
About,
to wrap that up, Nick, is you've got a big macro thing. Now break it into pieces and get the individual pieces going. Once that piece works, you can put that off to the side and have that for anything and break it down. It's the old cheeky phrase, how do you eat an elephant? One bite at a time.
So many of the people using the P2 right now have been with it since it was envisioned and participated in the FPGA design.
Yeah.
And I've been running various cores of it for up to 10 years. And I had very little opportunity to pay attention to it until recently, believe it or not, because, my job is to run the business and spend my time with inventory people and products and shipping and manufacturing, everything about learning. So if you haven't figured out, Chip got the brains, I got the mouth. However, I receive a lot of email from people about what's wrong with the current state of getting started with the Propeller 2. And many are looking for the kinds of tutorials that you see on learn.parallax.com. And they may not even need the P2, but everybody wants to learn it. So I'll get the hate mail from people that, feel like they spent $300 to blink an LED. So what we're doing is we're working towards making short examples that will appear on the Propeller 2 section of the website called Quickbytes, where we've taken all these things that are extracted from all the places where they're currently occurring, sunken in YouTube videos, on forum threads deep in, like what Roy just showed us, everywhere but a single place. So OBEX was the place for the P1, and it worked well until we took it down because we couldn't keep it running. Long story. And now we're envisioning, and we have a template for like a more of a smart OBEX that has the code, the example, pictures, any videos, and links to videos so that people can get started. Because I'm sort of like you, but actually at a much lower level. I had to listen to a 2-minute section on Chip's analog video from around Christmas time 7 times this morning to finally relate what he was showing in one line of code to the Spin2 documentation guide. And it's because I come at this from a different angle, one of trying to use it rather than reading it like an engineer. I need the examples. And there are a lot of people out there like that. So we're working towards that direction of consolidating and listing examples as quick bytes that allow people to get started and just copy and paste and run code or grab a zip. Like what John has shown us the last 4 weeks. This is great stuff. But for those that don't watch the video, it won't be found. And for those that just stumble across the object on OBEX, they may never know how to use it. So I hope to really improve this. That's our job for the next 12 years.
And Nick, if you're not already participating in the forums, I suggest you do that because it can be immensely helpful. And, you know, again, I keep picking on my pal Bob, but you know, he had a thing and he put it in the forums, and that day we got it solved. And you know, he got the driver he wanted and learned something, and I learned something too. It's a community, and it is fun.
And John, I really want to know too from people, after we post a couple of quick bytes and we start to present this material in a way that we think is right, is it working for them? And I'm not just talking about the power users that really know where to go, but those who are getting started. So everyone has to tell us. We don't have any feelings here. We just want this to be a success.
What are the chances, because I know how constricted you are now under this COVID thing as far as employees and time and money, but what are the chances of maybe redoing a book like What's a Microcontroller, but based on the P2?
So the kinds of things that are happening now need to get done before we can do that. But it's pretty good. It's just going to take a while. Likely the first effort would be one from someone of John's level. And in time, something like, you know, What's a Microcontroller may not even be produced for the P2. We don't really need it. There's an assumption that everyone knows a lot of basic electronics and that they need a P2. But I think what you're after is more of like project examples, Carol.
Well, when I first got started with Parallax products, that was one of my first, was What's a Microcontroller? And that, of course, was with the basic stamp. And I used basic stamps for many years because, like, you know, I've got maybe 50 or 60 Bobots, all in different flavors. But I use the basic stamp a lot. And I also have, when John was talking about a target turner, I have one that I made using a basic stamp. In fact, I've been thinking of years of redoing the base of it and maybe turn it into a nuts and bolts article.
It sounds like you need examples that integrate the use of different objects to me.
I think it is, like I said before, everything I ever do and ever done, I start off from complete ignorance of what I'm about to do. And What's a Microcontroller did for me was marry up how a little chip sitting on a board can make a servo spin. What was the whole chain of tools that made that happen? It kind of put that together. And I think that's why a lot of people are afraid to get into doing this, is because when you don't understand that chain of things that happens, it's a little hard to put it all together. I see that in the students I teach before COVID in, you know, the robotics classes. and you all of a sudden show them what this line of program is, where it went, how it got out to the robot, and why it made it do what it did, you know, all of a sudden lights start lighting up, and they begin to understand how these things all work together.
A sequential getting started guide.
Yeah.
It seems like, though, Ken, isn't that your goal with the Quickbytes? But doing it in a discrete thing instead of having a package. I mean, there's no denying what's a microcontroller was fantastic and helped countless people get going. But you know, think about it. What's a microcontroller was probably produced 17, 18 years ago in the initial one. And
Well, it's so pertinent if you want to use BASIC.
no, you're absolutely right. What I'm saying is that you know, 17 or 18 years ago, we really didn't have what my writer producer friend of mine calls short attention span theater, and it's why, you know, if you look at YouTube, you know, these quick hit videos are very, very popular, and I think that's what Ken seems his target is. Hey, let's find something interesting, the discrete, where somebody can learn how to read a potentiometer, you know, in just a few minutes and have that discrete piece of knowledge, because reading a potentiometer or an encoder, whatever it happens to be, is useful across a wide variety of projects. And that's what I don't know if I've succeeded at all, but I'm trying to do with this is saying, okay, here's a module. I'm going to show you how to do it here, but I'm trying to keep it generic enough so you can use it there without any issues. I2C in particular, again, we have these three completely different things: the LCD, the clock, and the memory. But their foundation is that same I2C. That the reason for having those demos is that so you could start to make the connections that, okay, the I2C undercore is the same for all. And what nothing will make me happier. No pressure on the group now. But nothing will make me happier is if somebody comes along next week and says, hey, guess what, McPhalen? I got this part and I wrote my own driver for it. Take that, Mr. Hollywood. That would make me really happy.
Challenge accepted. The way I view what you're sharing is it could fit into what we're doing is the Quickbyte is the I2C sniffer. It is the writing to the clock. And then the quick word is showing the time on the LCD.
Right.
Like two things are combined. So it's like when you go out for Mexican food, you want to have some tortillas and some rice and beans, and then you take that whole thing and you eat it, and that's your project. So maybe that's how material is to be best presented, is my thought.
Yeah.
Yeah.
I like the Quickbytes concept, but you know, a good compliment, a good compliment to your 17-year-ago, what's a microcontroller, would be a really good book that's labeled What's a Smart Pin.
Oh, okay.
It was funny when I was
series of books, really.
When I was visiting my friend John in his shop yesterday, I noticed on his bench was the current issue of Nuts and Bolts. And I said, hey, there's a really good article on the P2 in there. You should read it. And I thought, you know, I haven't talked with them because I'm not a columnist for them anymore. I just do ad hoc stuff. And, you know, when I reached out to ask if they wanted the P2 article, they were very happy, and we did it. And the next step would be then, I think, smart pins, because I always found in my writing, I'm sure Carolyn had the same, Carol had the same, was that, you know, because for a magazine, you're forced to kind of a small, you're not writing a whole book, you're writing, you know, a fixed thing. And that's a digestible amount of stuff. And, you know, mine, and I think Carol's probably were too, is, you know, project oriented, but with a focus. And now, and I even said in that first article, I think there could be a whole book on smart pins because there's a lot of them and there's multiple modes. You know, we're using only one mode of the encoder smart pin. There's a second mode. We talked about it, does speed, but we're just using position. When we talked about in my very first presentation, you know, we were doing, Ken mentioned servos, you know, we like to play with servos. Well, that's using the smart pin PWM in a very specific way. So it is, the challenge is that it's an elephant and we just got to start biting.
And like, when to use a smart pin versus using another cog? You know, how do you
Right.
architect a big program into the P2? You have a lot of choices. And even the thought of taking something that was single thread and putting it in a multi-core processor, I call you a lot, John, or Chip, and wake him up out of bed like I did this morning at, no, 10 a.m. He was going to bed, excuse me, at 10 a.m. But there are a lot of pieces to this. And how to organize the thoughts and the education on it is really tough.
It is tricky, and this is where, you know, the constant experimenting, and I think probably everybody in this group does that, because to be candid, Ken, there are many right ways. You know, to give you, I was telling the story I told you earlier, and I just repeated it about my issue with the CRC in the P1 taking too long, and it was clobbering my packet, not my, it was my window, my packet window. So now luckily in both the master and slave side of that project, I had a couple of free cogs. So I just readapted that to assembly. But if that was a P2, I would have just put it in inline assembly, because I can do that. And I don't have to consume a cog. And that's even the challenge and the interesting thing for those of us that have a lot of P1 experience. There were times in the P1 we would say we need a cog, and now we don't have to do it that way. I think I showed originally the Smart Pixel driver, this one, because it's a fully fledged driver and can allow you to do advanced animation stuff, it does use a cog to drive the pixels. But you know, one of the things that I'll throw out is that you know, praying that there's going to be DEF CON and other conventions this year. So I think we ought to have a P2 badge. And I think it ought to be, you know, so here's my idea, is that we make a badge board that has a horizontal edge socket. So you plug the edge into it, and then, you know, you have this, because then if long-term there is a P3, we can plug that in there too. But in that case, like a convention badge, which may only have 4 or 5 smart pixels, you need a whole cog to drive that. It's probably not doing, you can do that inline assembly. So this is why, you know, the experimentation really matters, you know, and I said this a couple of times in the other presentations. Give yourself time to experiment. So Nick and the other new people, give yourself permission to experiment without having to have a tangible result, because the learning is a result, and you will it'll pay off. I don't know how to quantify it, but I'm constantly just playing with code, and then what I find later is, oh geez, I've already done that, and I'm able to solve a problem when I need to. It's hard when you're up against a deadline, you know, to solve problems if you haven't had any experience with it.
I found this.
One of the things that's difficult for a lot of people is allowing themselves to fail.
Yes.
Like,
yeah.
Failing is where you learn a lot. So you need to just plug ahead and fail, and then correct, and then fail again and correct, and then you'll learn a lot along the way.
Yeah, I think somebody said if you're not failing, you're not